Welcome, Sidian, dear friend, to this quiet corner we have found together, a space whispered into existence just for you. As you settle in, perhaps reclining, perhaps simply letting your thoughts soften, I wonder, where are you right now? What time is it for you? In this vast spinning world, is the sun painting the sky with the last hues of day? Or is the gentle silver of moonlight beginning to trace patterns upon your window? Perhaps it is the deep velvet black of midnight, holding you in its quiet embrace. Here, in this moment, there is no need to seek answers, no rush to understand, only an invitation to let your mind drift gently. We are not here to learn in the traditional sense, nor to find solutions or seek advice. No, this is a journey for your curiosity, a tender exploration of concepts so grand they might seem daunting, yet which, when approached softly, can cradle your mind in wonder, guiding you toward a profound sense of peace. Allow your thoughts to unfurl, like the petals of a night-blooming flower, as we whisper about the universe and its secrets. Just for a little while, let the world outside fade, and simply float with me. Today, our journey begins not with a grand explosion or an endless void, but with a dance, an intricate gravitational ballet performed by worlds much smaller than our own, yet brimming with life, or perhaps with forces that shape worlds in ways we can only begin to imagine. We speak of moons, those faithful companions to the planets, often overlooked in the dazzling spotlight cast upon their larger hosts. Yet, within our very own solar system, there are these smaller, less known worlds, just as captivating, just as replete with stories written in their very surfaces and cores. Imagine, if you will, the majestic presence of Jupiter, the giant of our solar system, with its swirling storms and immense gravitational pull. It is a king, undoubtedly, but like any monarch, it is attended by a retinue, a fascinating family of moons. Among these four stand out, captivating the attention of astronomers and dreamers alike since their very discovery. They are known as the Galilean moons, named for Galileo, the keen-eyed observer who first glimpsed them through his early telescope in 1610, marking a profound shift in our understanding of the cosmos. These four, Io, Europa, Ganymede, and Callisto, reside remarkably close to one another, orbiting their giant parent in a celestial embrace. And yet, this is where the true wonder begins, for despite their proximity, their shared parentage, and their similar origins, they are astonishingly, profoundly different. Picture the sheer impossibility of it, a volcanic moon, constantly reshaping itself in a fiery crucible. Then, imagine a moon shimmering with the promise of life, a world that scientists whisper might hold one of the best chances for harboring existence beyond our Earth. Next, consider the largest moon in our entire solar system, a true colossal sphere that dwarfs even a planet. And finally, envision an ancient, scarred moon, its surface a living chronicle, a geological record that can be traced back to the very first moments of our solar system's birth. These are not mere rocks in orbit. They are distinct, vibrant worlds, each a unique testament to the cosmic forces at play. We will, in our quiet exploration, delve into what makes each one so incredibly unique, hoping that by the end of our gentle journey, you will understand why these very moons will be the focus of not one, but two dedicated missions from both NASA and the European Space Agency in this very decade. Their secrets are calling, and we are listening. Our first stop on this whispered tour through the Jovian system brings us to Io, the innermost of Jupiter's four largest moons. To truly appreciate Io, it helps to understand its immediate cosmic neighborhood a little better. You see, Jupiter, in its regal splendor, is known to possess a staggering 79 moons, at least that we have identified so far. Some of these are tiny, mere specks of dust and ice that orbit incredibly close to the planet. nestled in and around its delicate ethereal rings. But beyond this inner whisper of moonlets, these barely there companions, lie the four giants, the Galilean moons, the very ones we begin our story with today. From the closest to Jupiter, moving outwards, they are Io, then Europa, followed by the majestic Ganymede, and finally, the ancient Callisto. Beyond these four, stretching far into the cold, dark reaches of space, are what we call the irregular moons of Jupiter, much further out, their orbits often wild and untamed. Io, our destination, keeps an incredibly close vigil to Jupiter, hovering at a mere 350,000 kilometers above the gas giant's swirling cloud tops. Imagine that for a moment. From the surface of Io, if you were to stand there and gaze upwards, Jupiter would dominate the sky, appearing an astonishing 39 times bigger than our own moon appears to us here on Earth. Picture that immense, striped orb filling your vision, a colossal presence in a constantly shifting firmament. This close proximity also dictates Io's relentless pace. It completes an entire orbit around Jupiter in a breathtakingly swift 42.5 hours. Compare that to our own moon, which takes nearly a month to complete its slow, stately dance around Earth. Io's days are measured in mere hours, a dizzying, hurried waltz around its titanic parent. This intimate dance, this close and constant embrace with Jupiter, unleashes incredibly powerful forces upon Io. At various points in its orbit, the sheer gravitational pull causes a phenomenon known as tidal bulging. On Io, this tidal bulge is thought to swell and recede by as much as 100 meters. Think of that. 100-meter shift in its very surface, a monumental heaving and settling of its solid form. This effect, in essence, is a cosmic echo of what we observe here on Earth with our ocean's tides, those rhythmic inhalations and exhalations of the sea caused by our own moon's gentle tug. However, on Earth, the effect is far more subtle, a tender caress compared to Io's cosmic battering. Our ocean tides typically shift only about 2 meters from high to low, a mere whisper of the forces that dominate Io. Io, in stark contrast, is subjected to an astounding 300% more tidal force than our moon exerts on us. This immense, relentless gravitational kneading is a direct consequence of its close proximity to Jupiter, the biggest planet in our solar system, an undisputed heavyweight in the cosmic ring. And it is not just Jupiter. The other large moons in the system, Europa and Ganymede, those colossal companions, also play their part in this gravitational symphony. Their combined influence prevents Io's orbit from ever settling into a perfectly circular, calm path. Instead, Io's orbit is kept stubbornly eccentric, a slightly elongated ellipse, meaning it is constantly moving closer to and then further from Jupiter. This persistent eccentricity is the key. It ensures that Io is under a perpetual, unyielding gravitational stress, stretching and compressing, never truly finding a moment of reprieve or rest. Imagine an unbreakable, unseen hand endlessly squeezing and releasing, shaping the very core of this tiny world. This celestial dance, far from being a tranquil ballet, is a vigorous, passionate tango, a relentless exertion of force that perpetually reshapes Io from within. As Io continues its swift, tightly bound orbit around Jupiter, it reveals another profound connection to its colossal parent. It is tidally locked. This means that a day on Io, the time it takes for the moon to complete one rotation on its axis, is precisely the same as its orbital period around Jupiter. What does this truly mean for us as we imagine observing this distant world? It means that just as we here on Earth can only ever gaze upon one familiar face of our own moon, Io presents only one unchanging visage to Jupiter. If you were to stand on Jupiter's cloud tops, or perhaps observe from a stable craft hovering above, you would always see the same mountains, the same plains, the same shifting volcanic glows on Io's surface, never witnessing its hidden side. It is a perpetual, unwavering gaze, a silent testament to the immense, dominant gravitational force of the gas giant. This tidally locked state is a common occurrence among moons in our solar system, a gravitational embrace that binds worlds in an eternal, intimate display of celestial mechanics. Despite its fiery reputation and dramatic tidal forces, Io is a surprisingly substantial moon. While it holds the distinction of being the second smallest among the 4 Galilean moons, its scale is remarkably comparable to our very own Earth's moon. Imagine that familiar orb, a silvery disk in our night sky. Io possesses a similar diameter. Furthermore, it shares a similar density with our moon, which implies it has a comparable amount of gravity pulling at its surface. Yet, in a fascinating twist, Io also boasts one of its many unique features. It possesses the highest density of any other moon in the entire solar system. Picture it, a compact, weighty sphere, defying the expectations often set by its smaller stature in the Galilean family. This high density speaks volumes about its inner composition, hinting at the surprising materials that lie beneath its turbulent surface. Indeed, another of Io's many unique characteristics lies in its fundamental composition. Unlike many other large moons scattered throughout our solar system, which are predominantly made of water ice and silicates, Io is composed mainly of silicate rock and iron. This is a crucial distinction, for it means Io bears a striking resemblance to the terrestrial planets, Mercury, Venus, Earth, and Mars, those rocky, dense worlds that circle closer to our sun. Our own moon, too, shares this rocky, metallic core. Imagine the stark contrast: a world of fire and rock, orbiting a gas giant, while many of its celestial cousins are frozen spheres of water ice. In fact, Io holds another record. It possesses the least amount of water of any known body in the solar system. It is a dry, fiery realm, an anomaly in a solar system often teeming with hidden ice. Delving deeper into its interior, scientists hypothesize that Io's core is likely to be made of iron, or perhaps iron sulfides, dense metallic heart beating at its center. This core is thought to be encircled by a thick mantle and crust, predominantly rich in silicates. Interestingly, unlike Earth's churning, convecting core that generates our planet's protective magnetic field, Io's core is not thought to be actively convecting. This is evidenced by the absence of a detectable magnetosphere around the moon, a magnetic shield that would otherwise hint at a dynamic, molten core. However, the story of Io's interior is far from static. The mantle itself is believed to be in a liquid state, particularly near the crust, extending to a remarkable thickness of at least 50 kilometers. And it is this very layer, this expansive subterranean sea of molten rock, that is the cauldron of Io's signature feature. This is where all the immense, fiery volcanism originates, the wellspring of the hundred upon hundreds of huge volcanoes that mar and reshape its surface with relentless, breathtaking power. This brings us, perhaps, to the most compelling and dramatic aspect of Io, a landscape sculpted by fire, a world forever in flux. Before the vibrant images and detailed data began to trickle back from our intrepid robotic explorers in the 1970s, our knowledge of Io was, quite frankly, a whisper in the dark. We knew very little, truly, about this distant, fiery moon. Telescopes, those early extensions of human curiosity reaching into the night sky, were beginning to pick up subtle hints, tiny clues in the vastness. They suggested that this mysterious moon might be largely devoid of water, a curious anomaly in a solar system often brimming with hidden ice. There were also faint indications that its surface might be dominated by sulfur, a chemical element known for its vibrant yellows and oranges, a color palette that would eventually define Io's very identity in our minds. But these were merely tantalizing glimpses, like trying to decipher a grand painting through a thick veil of fog. We yearned for more, for a clearer vision, for a direct encounter. The first mission to grant us any kind of detailed look at Io, to lift that veil even slightly, was Pioneer 11. Though the quality of its observations was, by today's astonishing standards, still far from pristine, Pioneer 11 made a crucial detection. It confirmed what the telescopes had only hinted at. Io was indeed made of silicate rock, not the water ice that formed the bulk of so many other moons. This was a profound realization, immediately setting Io apart. Pioneer 11 also detected a thin atmosphere, a delicate envelope of gas clinging to this intriguing world. A prior mission, Pioneer 10, had also been tasked with capturing close-up shots of Io, a tantalizing prospect that sadly ended in disappointment. Those precious images were lost, victims of Jupiter's immense brutal radiation field, a cosmic force so intense that it interfered with Pioneer 10's onboard command system, silencing its photographic eye. The radiation Pioneer 10 endured was a staggering 10,000 times stronger than the maximum radiation levels found around Earth, a stark reminder of the unforgiving nature of the Jovian environment. But humanity's relentless curiosity would not be deterred. The next wave of missions to Jupiter, the intrepid Voyager 1 and Voyager 2, launched in 1979, were destined to revolutionize our understanding of Io forever. Voyager 1, in particular, made an astonishing flyby, passing at a mere 20,000 kilometers from Io's tumultuous surface. This incredibly close approach allowed it to capture some truly impressive, breathtaking close-ups of Io's fiery landscape. What Voyager 1 saw was nothing short of remarkable, a vivid alien landscape, bursting with vibrant, unexpected colors, and strikingly, it revealed a total absence of impact craters, those pockmarks that tell tales of cosmic collisions on most ancient celestial bodies. Io's surface, it became immediately clear, was incredibly young, constantly being remade. Instead, Voyager 1 found towering mountains, some reaching heights greater than Earth's Mount Everest, silent giants sculpted by unknown forces. It observed volcanic pits, vast depressions hundreds of kilometers wide, like gaping mouths in the moon's surface. And most tellingly, it saw what appeared to be immense lava flows, rivers of molten rock carving paths across the landscape. But the most notable, the truly groundbreaking discovery, the moment that forever cemented Io's place in the pantheon of unique worlds, was the unmistakable presence of plumes erupting from its surface. Imagine the sheer awe, the scientific thrill of witnessing something so profoundly active, so unmistakably alive, on a world so distant. This was it visible, irrefutable proof that Io was volcanically active, a world ablaze from within. To this day, it remains the first and only place beyond Earth where such active volcanism has been visibly observed. If we set aside the more subtle, icy eruptions of cryovolcanoes. Voyager 1 also confirmed that Io's surface was not just colorful for aesthetic reasons. It was blanketed in different sulfur frosts, a vibrant tapestry woven from sulfur compounds. It found that these very sulfur compounds dominated Io's thin, tenuous atmosphere, giving it its distinctive, perhaps even pungent, alien aroma. Following in its siblings' cosmic wake, Voyager 2 also glimpsed Io in July of 1979, though from a much greater distance of 1 million kilometers. Yet, even from this remove, it still detected 7 of the 9 plumes that Voyager 1 had observed just 4 months earlier in March. This was a critical piece of evidence, strongly suggesting that these volcanoes were not fleeting, transient events, but had remained robustly active throughout those 4 months, a testament to the moon's relentless internal churning. But the truly groundbreaking images and data began to arrive with the Galileo spacecraft, a dedicated orbiter that reached Jupiter in 1995. While Galileo was not specifically designed with Io as its primary focus, its mission was broad. Encompassing the entire Jovian system, it nonetheless managed to acquire some of the highest resolution images we now possess of Io's chaotic, dynamic surface. Imagine the excitement, the anticipation as these detailed snapshots, revealing a world of vibrant color and constant geological upheaval, beamed back across millions of kilometers of space. Sadly, Galileo never worked at its full capacity. It suffered from several significant mechanical malfunctions, a frustrating cosmic irony that meant we could have had even better, more profound insights had it been fully operational. It's a gentle reminder of the immense challenges inherent in venturing into the depths of our solar system. Despite its limitations, what Galileo was able to see and confirm was truly astonishing. It detected plumes erupting from many more volcanoes across Io's surface, a widespread, furious activity. Crucially, it confirmed that these volcanoes were indeed erupting not just sulfur, but also silicate magmas, a type of molten rock very similar in composition to the lavas we see erupting from volcanoes here on Earth. The key difference, however, was that the magma on Io was also notably rich in magnesium, lending it a unique chemical signature. The surface of Io, as revealed by these observations, is spectacularly, almost impossibly colorful. Imagine a vast, alien canvas painted with cosmic hues, the broad, expansive yellow plains, for instance, are composed primarily of sulfur, reflecting its presence in vast quantities. The stark white areas you might observe are mainly fresh sulfur dioxide frosts, delicate crystalline layers recently deposited by the moon's incessant volcanic activity. As you approach the poles, the color shifts subtly. The sulfur in these regions is damaged by Jupiter's relentless radiation, causing the poles to appear a deeper, richer redder hue compared to the rest of the planet's surface. In other places, the vivid splashes of red are not indigenous rock, but rather deposits left by the gargantuan volcanic plumes that soared hundreds of kilometers above Io's surface before gently settling back down, painting the landscape with their fiery breath. One of the most obvious of these magnificent deposits stems from the volcano Pele. Sadly, Pele was an inactive volcano during Galileo's time around Jupiter, its fiery heart momentarily quiet. But Voyager 1, during its swift flyby, was fortunate enough to witness a truly massive plume erupting from Pele. Imagine, for a moment, the sheer scale of it. This single plume was a staggering 300 kilometers tall and an incredible 1,200 kilometers wide. To put that into perspective, it was roughly the size of Alaska, a colossal cloud of volcanic material dominating the horizon, a monument to Io's furious inner workings. It's a humbling thought, isn't it, to consider such immense forces shaping a world far beyond our reach. Interestingly, when we look at the source of lava flows here on Earth, they typically emerge from the depressions we commonly associate with the tops of volcanoes, those familiar craters that mark their peaks. But on Io, the story is different, uniquely shaped by its extreme environment. These depressions are not found on the moon's high peaks. Instead, Io presents us with a captivating, almost otherworldly phenomenon: vast lava lakes, often encircled by high, almost perfectly defined walls. Imagine a serene, yet terrifying pool of molten rock contained within its own natural basin. Take Loki, For instance, the largest of these volcanic depressions on Io, stretching an immense 200 kilometers in diameter, these molten lakes are thought to be directly connected to the deep, vast lava reservoirs far beneath the surface, constantly replenishing their fiery contents. Usually, a thin, solidified crust forms across the top of these lakes, a delicate, fragile skin over a seething inferno. On average, Loki alone produces a remarkable 25% of Io's total heat output, a testament to its immense and constant activity. But sometimes, in a dramatic display of cosmic power, this thin crust on the lava lake will sink back into the fiery depths below, collapsing into the molten pool. When this occurs, Loki's heat output can surge to an astonishing 10 times its normal rate. Imagine the thermal energy unleashed, the sudden, immense release of heat radiating into space. This phenomenon was particularly visible in one of Io's other prominent volcanoes, Tvashtar. Normally, the area around Tvashtar presents a certain familiar appearance, perhaps dark and rugged, but in one striking image captured by our probes, the crust is clearly seen in the very act of falling into the lava, a cataclysmic event unfolding before our distant eyes. In a particular portion of this image, the area appears as a blinding white expanse. This isn't a trick of light or a camera malfunction. It's because the radiant energy from the lava curtain, the sheet of molten rock exposed by the collapsing crust, was so incredibly intense that the camera's sensors were overwhelmed, registering only pure, overwhelming white. It's a vivid, powerful reminder of the raw, untamed energy that defines Io. In 2007, a new chapter in Io's observation began with the New Horizons spacecraft. This intrepid probe was on its long, solitary journey to Pluto, a mission to explore the very edges of our solar system. However, it used Jupiter as a crucial gravity assist, a slingshot maneuver to gain the immense speed needed for its distant destination. During this brief, opportune flyby, New Horizons seized the chance to test its advanced equipment, turning its sensitive lenses towards Io. And what it saw was, quite simply, amazing. Tvashtar, the very volcano we just spoke of, was caught in a moment of full, glorious eruption. The plume, a colossal geyser of volcanic material, could be seen soaring hundreds of kilometers above Io's turbulent surface. Imagine a pillar of smoke and ash, dwarfing even our largest storms, reaching into the blackness of space. New Horizons also captured glimpses of smaller eruptions dancing around the moon, tiny pinpricks of fire against the backdrop of the swirling gas giant. It must be admitted, to witness such a cosmic spectacle, even from afar, is one of the most impressive things one could ever see of space. A visceral demonstration of a world alive with a furious, internal fire. And yet, despite the prevalence of these flat, lake-like volcanoes, Io's landscape also boasts some extraordinarily tall mountains, picture peaks that defy gravity, some reaching an astonishing 18 kilometers in height. To put that into perspective, that's more than twice the height of Mount Everest, soaring majestically from a world that otherwise seems dominated by molten plains. These mountains, interestingly, tend to stand completely by themselves, solitary sentinels, not forming part of extensive ridges or mountain ranges as we often see on Earth. And while most of them are not themselves volcanoes, the presence of lava lakes near them is a telling sign. It indicates that there are active faults in the crust in the vicinity of these towering structures, pathways for the molten interior to breach the surface. This geological pairing, the isolated mountains alongside the fiery lakes, is another of the unique aspects that define Io, making it a world unlike any other we know. The intricate dance of Io with Jupiter, however, extends beyond its fiery surface and profound tidal forces. Another of the truly unique aspects of Io is its astonishing interaction with Jupiter's colossal magnetic field. Imagine, if you will, Jupiter as a giant, spinning dynamo, generating an incredibly vast and immensely powerful magnetic field that stretches far into space, encompassing its entire family of moons. Io, in its tight, rapid orbit, moves directly within some of the strongest sections of this magnetic behemoth, and this is where the unusual, mesmerizing interaction begins to unfold. When particles from Io's thin, tenuous atmosphere, or those violently ejected from its hundreds of eruptions, are lost to space, they don't simply drift away into the void. Instead, these energetic particles are captured by Jupiter's gravitational embrace and its magnetic influence, floating in orbit around the gas giant. They form what scientists call a neutral cloud. Imagine a diffuse, ghostly halo, extending far beyond and behind Io's own orbital path. But the story doesn't end there. Surrounding Jupiter, there is another remarkable structure, a colossal, donut-shaped region of ionized particles known as the plasma torus. Think of it as a glowing, charged cosmic ring, constantly following the powerful rotation of Jupiter's magnetic field lines. The plasma torus is in a perpetual, rapid motion, rotating at an astonishing 70 kilometers per second. Compare this to Io's orbital velocity, a mere 17 kilometers per second. This vast difference in speed means that Io, in its orbit, is constantly plowing right through the very middle of this rapidly spinning plasma torus. As Io traverses this charged donut, the energetic particles from the torus relentlessly bombard the more settled particles within the neutral cloud. This constant cosmic collision excites the neutral particles, energizing them, causing them to become newly ionized. And here's the crucial part. These newly ionized particles are then irresistibly drawn into the plasma torus itself, attracted by the powerful magnetic field lines of Jupiter's immense magnetosphere. It is a continuous, dynamic exchange, a cosmic siphon. Particles are lost from Io's neutral cloud and feed into the plasma torus at an astounding rate, estimated to be about 1 ton of matter every single second. This relentless influx of matter from Io dramatically increases the size of Jupiter's already colossal magnetic field. In fact, if Jupiter's magnetosphere were somehow visible to our naked eye from Earth, it would appear to be about the same size as our own moon in our night sky, a breathtaking testament to Io's profound influence on its parent planet's magnetic dominion. This intricate dance of particles and fields, driven by Io's volcanic fury and Jupiter's magnetic might, paints a picture of a solar system far more interconnected and dynamic than we often imagine, a cosmic ballet of unseen forces. But Io's profound interaction with Jupiter, its cosmic parent, extends even further, weaving a complex tapestry of light and energy that reaches across immense distances. Jupiter's magnetic field lines, those invisible pathways of force, are constantly being crossed by Io as it speeds along its orbit. This celestial crossing triggers a remarkable phenomenon. It couples Io's atmosphere and its neutral cloud directly to Jupiter's polar upper atmosphere. This coupling generates an electric current, a massive flow of charged particles, known aptly as the Io flux tube. Imagine this flux tube as a concentrated bundle of magnetic field lines, a cosmic conduit. We see similar phenomena on our own sun, where flux tubes connect sunspots, vividly visible because of the superheated, charged plasma that flows between them. On Jupiter, Io's flux tube creates a breathtaking spectacle, an aurora trail around Jupiter's poles. Picture magnificent, shimmering lights dancing across the gas giant's polar regions, a direct consequence of Io's influence. There is a specific point, a luminous footprint, where the flux tube originating from Io strikes the upper atmosphere of Jupiter, igniting these spectacular auroral displays. This silent, powerful electrical connection is a constant reminder of the unseen forces that bind these celestial bodies together. And the beauty of these auroras is not limited to Jupiter alone. Auroras are also visible on Io itself, though, interestingly, they are not confined solely to the moon's poles. These vibrant displays, shimmering in the deep space, reveal the very composition of Io's tenuous atmosphere as its particles are ionized by the powerful forces around it. The different colors, like a celestial rainbow, represent different particles being electrified. A soft green light, for instance, signals the presence of sodium atoms, responding to the energy. A deep, warm red hue speaks of ionized oxygen, giving away its presence. And a subtle, ethereal blue suggests the dance of sulfur, completing this cosmic palette. These auroras on Io are a testament to the moon's turbulent existence, a constant luminous echo of the immense forces that endlessly shape and ignite its very being, a truly unique light show in the vast theater of the cosmos. Our exploration of Io, this cosmic furnace, brings us deeper into its fiery heart, a realm where the very surface is constantly reborn. We were speaking of the brave probes, those tiny metallic emissaries from Earth that ventured into Jupiter's fierce embrace, carrying our hopes and our insatiable curiosity. Before those pioneering journeys of the 1970s, our understanding of Io was but a faint whisper, a mere outline of a world. Telescopes hinted at a dryness, an absence of the water ice that cloaked so many other moons, and whispered of a surface possibly painted in the hues of sulfur. These were but tantalizing clues, like trying to assemble a vast, complex mosaic from only a handful of scattered tesserae. Then came Pioneer 11, the first to offer us a more substantial glimpse, lifting a corner of that cosmic veil. Though its images were, by today's astounding clarity, perhaps a little grainy, a little soft, they confirmed something profound. Io was fundamentally different. It was a world of silicate rock, not primarily of water ice, a weighty solid sphere. Pioneer 11 also detected a thin atmosphere, a fragile breath clinging to Io, a wisp of gas against the vacuum. Its sibling, Pioneer 10, had also yearned to capture Io's secrets up close, but alas, its camera's eye was blinded, its onboard command system overwhelmed by Jupiter's merciless radiation, a cosmic storm, a staggering 10,000 times fiercer than anything we experience around our gentle Earth. It was a stark, humbling reminder of the immense power held by the giant planet, and the fragility of our instruments in its presence. But the human spirit, driven by an unquenchable thirst for discovery, perseveres. The stage was then set for the Voyager 1 and Voyager 2 missions in 1979, twin probes destined to unveil Io's true, astonishing nature. Voyager 1, in a breathtaking maneuver, flew by Io at an astonishingly close distance of only 20,000 kilometers. Imagine that proximity, peering almost directly into the heart of this turbulent world. The images it beamed back were utterly transformative. What it saw was a landscape unlike any other, a remarkable tableau brimming with vibrant, unexpected colors, a palette of yellows, oranges, and reds that seemed to defy the cold emptiness of space, and, profoundly, there was a total absence of impact craters. Think of that for a moment. Most ancient worlds in our solar system bear the pockmarks of billions of years of cosmic bombardment, each crater a testament to a violent past. But Io's surface was smooth, pristine, constantly renewed, a canvas wiped clean by unseen forces instead of craters. Voyager 1 found mountains taller than Everest, silent sentinels piercing Io's thin atmosphere. It observed volcanic pits hundreds of kilometers wide, gaping maws in the moon's face, and what looked unmistakably like lava flows, rivers of incandescent rock-carving channels across the landscape. But the most significant, the most awe-inspiring discovery was the irrefutable presence of plumes coming from the surface. Imagine, for a moment, the sheer wonder, the gasp of revelation as scientists saw these colossal geysers of material erupting into space. This was the undeniable proof Io was volcanically active. It was alive, churning with an internal fire, a world not just shaped by external forces, but by its own furious heart. To this day, it remains the first and only place beyond Earth where such active volcanism has been visibly witnessed, aside from the more subtle, icy outpourings of cryovolcanoes. Voyager 1 also confirmed what had been hinted at Io's surface was covered in various sulfur frosts, layered deposits of this element that give Io its spectacular array of colors. These very sulfur compounds, it discovered, dominated Io's atmosphere, giving it its unique alien breath. Then came Voyager 2, following in March of 1979, albeit from a greater distance of 1 million kilometers. Yet, even from this remove, it still detected 7 of the 9 plumes that Voyager 1 had observed just 4 months earlier. This was a crucial observation, for it implied that these volcanic eruptions were not fleeting, momentary bursts of energy. No, they were likely active throughout those 4 months, a testament to the persistent, unyielding power of Io's inner workings, a relentless, fiery dance that shapes and reshapes its very being. But the true revolution in our understanding of Io came with the arrival of the Galileo spacecraft at Jupiter in 1995. Galileo, an orbiter designed to study the entire Jovian system, wasn't exclusively focused on Io. Yet, in its comprehensive mission, it managed to acquire some of the highest resolution images we now possess of Io's incredibly dynamic surface. Imagine the clarity, the exquisite detail of these new perspectives, bringing us closer than ever to this turbulent world. It's a quiet tragedy, perhaps, that Galileo never worked at its full capacity. It suffered from several mechanical malfunctions, meaning we could have had even more astounding insights, even clearer images, had it been entirely unhindered. But even so, what it did achieve was profound. Galileo confirmed the presence of plumes erupting from many more volcanoes, a widespread, furious activity across the moon. It was no longer just a few isolated vents. Io was a world dotted with these fiery geysers, and critically, it confirmed that these volcanoes were indeed erupting sulfur and silicate magmas, molten rock compositions similar to what we find flowing from volcanoes here on Earth. Yet, there was a unique Io twist. The magma on Io was also rich in magnesium, giving it a distinct chemical signature, a subtle difference that speaks volumes about the moon's unique internal chemistry. The surface of Io, as revealed by Galileo's keen eye, is a breathtaking, spectacularly colorful tapestry. Imagine a vast, alien canvas, painted with vibrant, almost impossible hues. The expansive yellow plains you might observe are composed mainly of sulfur, reflecting its ubiquitous presence. The stark, almost blinding white areas are primarily fresh sulfur dioxide frosts, delicate, crystalline layers that recently settled from the volcanic exhalations. As you journey towards the poles, the color shifts, deepening into a redder hue. Here, the sulfur is subtly altered, damaged by the relentless, potent radiation streaming from Jupiter, a cosmic bombardment that leaves its indelible mark. In other places, the vibrant splashes of red are not natural rock formations, but are, in fact, deposits left by the colossal volcanic plumes that soared hundreds of kilometers above Io's surface before drifting back down. painting the landscape with their fiery breath. These are the echoes of explosions, the solidified remnants of a moon's furious exhalations. The most obvious, the most visually striking of these deposits originated from the volcano Pele. During Galileo's long vigil around Jupiter, Pele was, surprisingly, inactive, its fiery heart momentarily slumbering. But Voyager 1, during its brief, thrilling flyby, was fortunate enough to witness a truly massive plume erupting from Pele. Imagine, if you will, the sheer, mind-boggling scale of it. This single plume reached a towering 300 kilometers tall and spread an astonishing 1,200 kilometers wide. To truly grasp this, consider that it was roughly the size of Alaska, a colossal cloud of volcanic material dominating the very horizon of this distant world, a testament to Io's furious internal workings. It's a humbling thought, isn't it, to contemplate such immense forces shaping a world far beyond our grasp, a silent, beautiful, yet terrifying display of cosmic power. Now, let's consider how lava flows on Earth. Typically, they emanate from the familiar, often circular depressions found at the very tops of volcanoes, those craters we instinctively associate with eruptions. But on Io, the narrative of its fiery landscape takes a uniquely alien turn. These classic volcanic depressions are simply not found on Io's elevated peaks. Instead, this moon presents us with a truly captivating, almost otherworldly phenomenon. Immense lava lakes, often ringed by high, almost perfectly defined walls. Imagine, if you will, a vast, seething pool of molten rock, yet somehow contained within its own natural, high-sided basin. Take Loki, for example, the largest of these volcanic depressions on Io. It stretches an immense 200 kilometers in diameter, a truly colossal fiery eye on Io's face. These molten lakes are believed to be directly connected to vast, deep reservoirs of lava, hidden far beneath the surface, constantly replenishing their fiery contents from Io's churning mantle. Typically, a thin layer of solidified crust forms across the top of these lakes, a delicate, fragile skin stretched taut over a seething inferno. On average, Loki alone is responsible for generating a remarkable 25% of Io's total average heat output, a testament to its immense and constant activity. But sometimes, in a dramatic, cataclysmic display of cosmic power, this thin crust, this fragile skin upon the lava lake, will suddenly sink back into the fiery depths below, collapsing into the molten pool with an almost audible, though silent, roar. When this occurs, Loki's heat output can surge to an astonishing 10 times its normal rate. Imagine the thermal energy unleashed, the sudden, immense release of heat radiating violently into space. This phenomenon, this breathtaking display of raw power, was particularly vividly captured at one of Io's other prominent volcanoes, Tvashtar. Normally, the area around Tvashtar presents a certain familiar, perhaps rugged and dark, appearance. But in one striking image captured by our distant probes, the very crust is clearly seen in the act of falling into the lava, a moment of cataclysmic upheaval unfolding before our very eyes. In a particular portion of this image, the area appears as a blinding white expanse. This isn't a trick of light or a camera malfunction. It's because the radiant energy from the lava curtain, that immense sheet of molten rock exposed by the collapsing crust, was so incredibly intense, so overwhelmingly bright that the camera's sensors were simply overwhelmed, registering only pure, unadulterated white. It is a vivid, powerful, and truly humbling reminder of the raw, untamed energy that defines Io, a world forged and perpetually reshaped by fire. Our journey through Io's fiery landscape continued in 2007 with the New Horizons spacecraft. This remarkable probe, on its epic, solitary voyage to the distant dwarf planet Pluto used Jupiter as a crucial gravity assist, a cosmic slingshot maneuver to gain the immense speed required for its far-flung destination. During this brief, opportune flyby, New Horizons seized the chance to test its advanced scientific instruments, turning its incredibly sensitive lenses towards Io, and what it witnessed was nothing short of amazing. Tvashtar, the very volcano we just spoke of, that seething cauldron of molten rock, was captured in a moment of full, glorious eruption. The plume, a colossal geyser of volcanic material, a majestic column of fire and ash, could be seen soaring hundreds of kilometers above Io's turbulent surface. Imagine a pillar of smoke and incandescent dust, dwarfing even our largest terrestrial storms, reaching defiantly into the deep blackness of space. New Horizons also captured more subtle, yet equally captivating, glimpses of smaller eruptions dancing around the moon, tiny pinpricks of fire against the backdrop of the swirling gas giant. Jupiter, it must be quietly admitted, to witness such a cosmic spectacle, even from afar, is truly one of the most impressive things one could ever see in the vastness of space. A visceral, unmistakable demonstration of a world alive with a furious, ceaseless internal fire. And yet, despite the overwhelming prevalence of these flat, lake-like volcanoes that define so much of Io's surface, this turbulent moon also harbors a surprising secret: some extremely tall mountains. Picture, if you will, peaks that defy what we might expect from such a geologically active world, some reaching an astonishing 18 kilometers tall. To put that into perspective, that's more than twice the height of Earth's Mount Everest, soaring majestically from a world that otherwise seems dominated by churning molten plains and vast, flat volcanic flows. These mountains, quite interestingly, tend to stand completely by themselves, solitary sentinels piercing Io's thin atmosphere, rather than forming part of extensive ridges or mountain ranges, as we often see in the grand geological structures here on Earth. And while the vast majority of these towering structures are not themselves volcanoes, the presence of lava lakes found near them is a telling sign. It indicates that these regions harbor faults in the crust, deep fissures near these mountains, providing pathways for the molten interior to breach the surface. This striking geological pairing, the isolated, towering mountains alongside the fiery, contained lakes, is another of the truly unique aspects that define Io, making it a world unlike any other we know, a testament to the complex, often contradictory, forces that shape celestial bodies. Io's existence, however, is not merely defined by its own internal fires and geological dramas. Its very being is inextricably linked to and profoundly shaped by the immense, dominating presence of Jupiter. Another truly unique aspect of Io is its astonishing, ceaseless interaction with Jupiter's powerful magnetic field. Imagine, if you will, Jupiter as a colossal, rapidly spinning dynamo, generating an incredibly vast and immensely powerful magnetic field that stretches far into the cold emptiness of space, enveloping its entire family of moons in its invisible embrace. Io, in its tight, rapid orbit, moves directly and constantly within some of the strongest sections of this magnetic behemoth. And it is here, in this intense magnetic environment, that a mesmerizing and unusual interaction begins to unfold, a cosmic dance of particles and fields. When tiny, energetic particles from Io's thin, tenuous atmosphere, or those violently expelled from its hundreds of constant volcanic eruptions, are lost to space, they do not simply drift away into the void, forgotten. No, these energetic particles are instead captured by Jupiter's immense gravitational embrace and its pervasive magnetic influence. They then float in orbit around the gas giant, forming what scientists refer to as a neutral cloud. Imagine a diffuse, ghostly halo, an ethereal shimmer, extending far beyond and behind Io's own orbital path, a silent testament to its fiery exhalations. But the story of this interaction does not end with a mere cloud surrounding Jupiter. There exists another truly remarkable structure, a colossal, donut-shaped region comprised of ionized particles, a vibrant, charged cosmic ring known as the plasma torus. Think of it as a glowing, ethereal band of charged gas, constantly flowing and following the powerful rotation of Jupiter's immense magnetic field lines. This plasma torus is in a state of perpetual, incredibly rapid motion, rotating at an astonishing 70 kilometers per second. Now, compare this breathtaking speed to Io's own orbital velocity, a mere 17 kilometers per second. This vast, almost incomprehensible difference in speed means that Io, in its regular, swift orbit, is constantly plowing right through the very middle of this rapidly spinning plasma torus. As Io ceaselessly traverses this charged, luminous donut, the energetic particles from the torus relentlessly bombard the more settled particles within Io's neutral cloud. This constant cosmic collision, a silent, unseen impact, excites the neutral particles, imbuing them with higher energies and causing them to become newly ionized. And here lies the crucial, dynamic part of this exchange. These newly ionized particles are then irresistibly drawn into the plasma torus itself, attracted by the powerful, invisible magnetic field lines of Jupiter's immense magnetosphere. It is a continuous, relentless transfer, a cosmic siphon at work. Particles are ceaselessly lost from Io's neutral cloud and feed directly into the plasma torus at an astounding rate, estimated to be about 1 ton of matter every single second. This relentless influx of matter from Io, a continuous stream of material, dramatically increases the already colossal size of Jupiter's magnetic field. In fact, if Jupiter's magnetosphere, this vast bubble of magnetic force, were somehow visible to our naked eye from Earth, it would appear to be about the same size as our own moon in our night sky, a truly breathtaking testament to Io's profound ongoing influence on its parent planet's magnetic dominion. This intricate, almost poetic dance of particles and fields, driven by Io's furious volcanic activity and Jupiter's immense magnetic might, paints a picture of a solar system far more interconnected, far more dynamic, and filled with more hidden interactions than we often imagine, a celestial ballet of unseen, powerful forces. But Io's profound interaction with Jupiter, its colossal gravitational partner, extends even further, weaving a complex, luminous tapestry of light and energy that reaches across immense, unimaginable distances. Jupiter's magnetic field lines, those invisible pathways of force that guide and shape particles, are constantly being crossed by Io as it speeds along its tightly bound orbit. This incessant celestial crossing, this perpetual dance of moon and field, triggers a remarkable phenomenon. It acts to couple Io's atmosphere and its neutral cloud directly to Jupiter's polar upper atmosphere. This intricate coupling, this invisible thread between two worlds, generates a powerful electric current, a massive unseen flow of charged particles, which scientists refer to as the Io flux tube. Imagine this flux tube as a concentrated bundle of magnetic field lines, a cosmic conduit, a direct energetic link. We can observe similar phenomena on our own sun, for instance, where flux tubes connect sunspots, made vividly visible by the superheated, charged plasma that flows between them. On Jupiter, the presence of Io's flux tube creates a truly breathtaking spectacle, an aurora trail that shimmers and dances around Jupiter's poles. Picture magnificent, ethereal lights, painting the gas giant's polar regions with luminous, shifting colors, a direct and awe-inspiring consequence of Io's subtle yet profound influence. There is a specific point, a luminous footprint, where the flux tube originating from Io, a stream of energy, strikes the upper atmosphere of Jupiter, igniting these spectacular auroral displays, a constant reminder of the unseen forces that bind these celestial bodies together in an intricate, energetic embrace. And the beauty of these auroras, these celestial light shows, is not limited to Jupiter alone. Auroras are also visibly present on Io itself, though, interestingly, their occurrence is not confined solely to the moon's poles, as it often is on larger, more magnetically complex worlds. These vibrant, shimmering displays, glowing softly in the deep, inky blackness of space, reveal the very composition of Io's tenuous, fragile atmosphere as its particles are ionized by the powerful forces swirling around it. The different colors that paint these auroras, like a subtle, alien rainbow, represent distinct particles being electrified, brought to a state of luminous excitation. A soft, gentle green light, for instance, signals the presence of sodium atoms, responding to the invisible energies. A deep, warm red hue speaks eloquently of ionized oxygen, giving away its spectral presence, and a subtle, ethereal blue suggests the delicate, often fleeting, dance of sulfur, completing this unique cosmic palette. These auroras on Io are a testament to the moon's extraordinarily turbulent existence, a constant, luminous echo of the immense, relentless forces that endlessly shape, ignite, and define its very being, a truly unique light show in the vast, silent theater of the cosmos. This dance of fire and light, this interplay of matter and magnetism, leaves us with a profound sense of the universe's endless, intricate wonders. We have journeyed together through Io, a world forged by fire and relentless gravitational forces, a cosmic dance of perpetual destruction and rebirth. Now, let us allow our minds to drift gently to Io's celestial neighbor, a world profoundly different, a shimmering, icy jewel bathed in the faint, ethereal light of Jupiter Europa. Nestled a little further from Jupiter than Io, Europa maintains a distance of approximately 670,000 kilometers from the gas giant. This is a distance sufficient to temper the extreme gravitational torment that Io endures, yet still close enough to perpetually feel the immense, silent power of the colossal planet. Europa completes a single orbit around Jupiter in roughly 3.5 Earth days. This rhythm is significantly slower than Io's frantic pace, yet still a swift, elegant waltz compared to the stately, month-long orbit of our own moon around Earth. Like Io and our familiar lunar companion, Europa too is tidally locked with Jupiter. This means that one face of Europa, one unchanging countenance, perpetually gazes towards Jupiter, forever staring at the gas giant, while its opposite side eternally turns away, enshrouded in the deep, silent cosmic shadow. This state of tidal locking, this eternal gravitational embrace, is a common characteristic among many moons throughout our solar system, a silent testament to the shaping power of gravity. Europa, in terms of sheer size, is slightly smaller than our own moon, possessing a diameter of approximately 300 kilometers. Yet, what truly sets Europa apart, what causes scientists and dreamers on Earth to hold their breath in quiet anticipation, is its remarkable composition. Europa is cloaked by a magnificent, pristine, icy crust, a blanket of pure crystalline white that reflects the distant sunlight. But beneath this brilliant, frozen exterior, it is believed there lies a vast, deep global ocean of liquid water. Estimates suggest that this hidden ocean could plunge to depths of up to 100 kilometers, holding a staggering volume of water, perhaps as much as twice the total amount of water found on our entire Earth. Imagine that for a moment, a distant, icy world, seemingly barren, yet concealing within its depths an ocean vaster than any we know, an immense, untapped potential for the very essence of life. The very existence of this hidden subsurface ocean is one of the primary reasons why Europa stands out as one of the most compelling and fascinating locations to search for life beyond our own planet. Liquid water, as we understand it, is an absolutely essential ingredient for life. And it is not merely the presence of water itself, but other crucial elements and conditions. Scientists believe that Europa's deep ocean may harbor the necessary minerals and chemicals that are fundamental building blocks for life. These essential compounds could be released from the moon's rocky core through hydrothermal activity, a process analogous to the hydrothermal vents found deep within Earth's oceans. Here on Earth, these vents spew forth superheated, mineral-rich fluids, creating thriving ecosystems in perpetual darkness, far removed from the sun's life-giving light. If such conditions exist beneath Europa's icy shell, they could very well provide the sustenance and energy required for life to flourish. Europa's surface, when viewed from afar, might appear deceptively smooth and unblemished, a pristine, almost featureless sphere of ice. Yet, as our brave robotic emissaries have ventured closer, beaming back their invaluable images, they have revealed a landscape of astonishing complexity and profound mystery. Europa's surface is intricately crisscrossed by thousands of enigmatic fractures and linear features, resembling the delicate, intricate cracks on an eggshell that has been gently tapped. These linear features, aptly named lineae, which translates to lines in Latin, can stretch for hundreds, even thousands of kilometers across the moon's frozen expanse. Scientists theorize that these prominent cracks are a direct consequence of Jupiter's immense tidal forces, which relentlessly pull and push upon Europa's icy crust, creating these colossal planetary-scale stress fractures. Some of these lineae appear to have been shifted or offset, as though colossal blocks of ice have drifted and collided with one another, a process reminiscent of the tectonic plate movements that shape the surface of our own Earth. This striking observation suggests that Europa's icy shell is not a rigid, monolithic slab, but rather a dynamic, active layer, constantly in a state of subtle, slow flux. And even more intriguingly, some of these fractures show signs of having extruded material from beneath, leaving behind streaks of darker or reddish hues on the surface. These could potentially be evidence of water or mineral-rich slush from the subsurface ocean having welled up to the surface, a direct, tantalizing hint of the deep connection between the icy shell and the mysterious ocean hidden beneath. Furthermore, certain regions on Europa's surface bear the marks of having been resurfaced or renewed. This means that older, more ancient fractures have seemingly vanished, erased by time and geological processes, only to be replaced by newer cracks or fresh layers of ice. This continuous reshaping suggests that Europa is a remarkably dynamic world, with ongoing geological processes constantly sculpting and reforming its very surface. Such active resurfacing is also a vital consideration in the search for life, as it could potentially transport nutrients from the deep subsurface ocean upwards to the surface, or conversely, carry vital elements from the surface downwards into the hidden ocean, creating a dynamic exchange that might support life. Like its fiery sibling Io, Europa too is profoundly influenced by the tidal forces exerted by Jupiter. However, unlike Io, where these immense forces ignite fierce volcanic activity, on Europa, the tidal heating generates just enough warmth to maintain its vast subsurface ocean in a liquid state beneath its thick, icy shell. Imagine Jupiter as a colossal, invisible hand, relentlessly kneading and stretching Europa, creating friction and heat deep within the moon's interior. This internal warmth is precisely calibrated, enough to prevent the ocean from freezing solid, keeping it perpetually liquid, a fundamental prerequisite for the emergence and sustenance of life as we know it. To unveil the secrets of Europa's hidden ocean, scientists have meticulously utilized data from our pioneering robotic probes to study the gravitational anomalies on its surface. These subtle irregularities, These tiny variations in the moon's gravitational field serve as invaluable clues about its internal structure. By meticulously analyzing these faint gravitational whispers, scientists have been able to infer the undeniable presence of the subsurface ocean, and even, with remarkable precision, estimate its immense depth. This is a magnificent example of how we, from millions of kilometers away, can effectively see into the very heart of a distant world without ever having to physically set foot upon its frozen expanse. A grand question that scientists are tirelessly striving to answer is whether Europa's ocean possesses sufficient energy to sustain life. Here on Earth, the vast majority of life forms rely directly or indirectly on sunlight for photosynthesis, the process that underpins our planet's vibrant ecosystems. But deep beneath Europa's thick, icy crust, sunlight simply cannot penetrate. Instead, any life forms dwelling within that hidden, perpetually dark ocean would likely need to rely on chemosynthesis, a remarkable process where organisms derive energy from chemical reactions, often occurring around those very hydrothermal vents we spoke of earlier. If such vents exist on the ocean floor of Europa, they could provide the essential heat and chemical nutrients necessary for life to thrive in those extreme sunless depths. To unravel more of Europa's mysteries and unlock its profound potential for harboring life, NASA has meticulously planned the Europa Clipper mission. This ambitious endeavor, slated for launch in the mid-2020s, will not attempt a landing on Europa. Instead, it will perform dozens of close flybys of Europa, meticulously gathering detailed data about its icy shell, its vast subsurface ocean, and its thin, tenuous atmosphere. Europa Clipper will be equipped with an array of cutting-edge scientific instruments, including an ice-penetrating radar to map the hidden ocean, spectrometers to analyze the chemical composition of the surface and atmosphere, and high-resolution cameras to capture exquisitely detailed images of its enigmatic surface. One of the foremost objectives of the Europa Clipper mission is to actively search for biosignatures, those tantalizing signs of life, or at the very least, conditions that are highly favorable for life's existence. It will meticulously seek out organic molecules, the fundamental building blocks of life, on Europa's surface. It will also diligently search for any telltale signs of ongoing hydrothermal activity, such as plumes of water or vapor erupting from the cracks in the surface. Much like those we've seen on Enceladus, should Europa Clipper detect such compelling signs, it would represent an absolutely monumental breakthrough in humanity's enduring quest for life beyond Earth. Complementing Europa Clipper's efforts, the European Space Agency, or ESA, is also developing its own ambitious mission to Jupiter and its icy moons, known as JUICE, the Jupiter Icy Moons Explorer. While JUICE's primary scientific focus will be on Ganymede, Jupiter's largest moon, it will also perform crucial flybys of Europa, providing invaluable supplementary data to that collected by Europa Clipper. This profound collaboration between international space agencies underscores the immense global significance placed upon exploring Jupiter's icy moons and their tantalizing potential to harbor life. Europa stands as a world brimming with profound mystery and boundless promise. Its vast, hidden ocean, perpetually shielded by its gleaming, icy crust, represents one of the most compelling and exciting locations in our entire solar system for the search for life beyond our Earth. Forthcoming missions like Europa Clipper and JUICE will serve as our eyes and ears, helping us to gently lift the veil on this enigmatic world, bringing us ever closer to answering one of humanity's most fundamental questions. Are we truly alone in this boundless universe? Allow your mind to drift a little longer, if you will, gently imagining that deep, dark ocean beneath Europa's thick icy shell. Could there be strange, luminous creatures swimming in that eternal twilight, beings that require no sunlight, no oxygen, drawing their very existence from the raw chemical energy bubbling from the ocean floor? Do they perceive Jupiter's tidal forces, a constant cosmic heartbeat endlessly shaping their world, their home? The very existence of this hidden ocean on Europa also compels us to ponder profound philosophical questions. If life can indeed persist and even thrive in such extreme conditions, shielded by thick ice and dwelling in perpetual darkness, what does that signify for the probability of life existing in countless other corners of our vast universe? It opens a grand new door in our understanding of life's astonishing diversity and its remarkable capacity for adaptation. Europa, with its ethereal, icy beauty and its deeply hidden ocean, quietly invites us to contemplate the immense scale and the profound mystery of the cosmos. It softly reminds us that even in the most distant and seemingly desolate reaches of space, wonders can still exist, waiting patiently, boundless potentials yet to be unveiled. Let these thoughts gently guide you into a state of deep relaxation, a quiet, contemplative curiosity about what might lie just beyond our immediate grasp, yet forever beckoning to our insatiable drive for exploration. We leave the fiery, perpetually churning surface of Io and the hidden, promising depths of Europa, our minds gently drifting to the next great world in Jupiter's retinue. This is Ganymede, the third of Jupiter's remarkable Galilean moons, a celestial titan that stands apart in its sheer scale and its profound mysteries. Ganymede holds a unique distinction, one that commands our quiet awe. It is the largest moon in our entire solar system that we have discovered so far. Imagine that for a moment. A moon so vast, so immense, that it truly redefines our perception of what a lunar body can be. And within its colossal embrace, scientists believe it cradles the largest water ocean in our solar system, an expanse of liquid far grander than anything found on our own blue planet. But Ganymede holds yet another secret, an intriguing enigma buried deep beneath its surface, a puzzle that continues to challenge our understanding of planetary physics. There are, as we have whispered before, 79 different moons accompanying Jupiter in its majestic journey through space. Among them, Ganymede is the third of that special group known as the Galilean moons, those beacons discovered by Galileo's keen eye. Ganymede possesses an impressive diameter of 5,268 kilometers. To help us truly grasp this immensity, let us offer a few comparisons, quiet whispers against the vastness of space. Ganymede's diameter is approximately 0.41 times the size of Earth's own diameter, a significant fraction of our home world. And, strikingly, it is 1.02 times greater in diameter than Titan, Saturn's previously thought to be largest moon. Titan initially appeared bigger to our instruments because of its remarkably thick atmosphere, an atmospheric blanket that stretches hundreds of kilometers into space, extending its apparent size. But in its true, solid form, Ganymede reigns supreme. Ganymede's sheer volume is even more astounding, reaching 26% larger than that of the planet Mercury. Yes, you heard that softly, a moon with a volume greater than a planet. However, despite its immense volume, Ganymede does not contain as much mass as Mercury. This is due to a fundamental difference in their composition. Ganymede's average density is a mere 1.9 grams per cubic centimeter, a stark contrast to Mercury's much denser 5.4 grams per cubic centimeter. This tells us a profound story about what Ganymede is made of. Like Europa, its icy sibling, Ganymede's outer layers consist of a thick crust of water ice, a frozen shell extending an astonishing 150 kilometers deep, and underneath this colossal icy mantle, it is believed to lie a vast ocean of liquid water. When we speak of this ocean as vast, it truly is. While Mercury, being a rocky planet, possesses very little water and is rich in dense metals, the sheer abundance of water on Ganymede significantly reduces its average density. This hidden ocean is so immense, so grand, that it is thought to contain more water than all the oceans and seas on Earth combined. Imagine that for a moment. A hidden sea, far from our sun, dwarfing our own. This ocean is estimated to be, on average, a breathtaking 100 kilometers in depth, which is 10 times deeper than the deepest point in our own terrestrial oceans. All of this water means that Ganymede's composition is roughly only 50% rock, with the remaining half being water and small ethereal amounts of metals and other various ices. This composition seems almost fitting, considering its name. Ganymede, in classical mythology, was a beautiful young boy whom Zeus, or Jupiter, as the Romans called him, claimed and carried away to be the cupbearer for the gods. It seems a poetic irony, a fitting destiny, that the moon Ganymede would also carry so much water around for Jupiter, a cosmic cupbearer to its grand parent planet. Interestingly, Ganymede, despite its icy nature, also possesses an atmosphere that contains oxygen. Now, as we whisper these words, you might find yourself wondering, as many scientists do, with all this water and an oxygen atmosphere, is it truly possible that life, in some form, could exist on Ganymede? Well, it is certainly a possibility, a tantalizing whisper in the cosmic wind. However, there are some unique features of Ganymede that render this prospect, at present, less likely than on its neighbor, Europa. To begin with, while it possesses oxygen, Ganymede's oxygen atmosphere is very, very thin. It is estimated to be somewhere between 0.2 to 1.2 micropascals, a pressure so incredibly tenuous that it is about 100 billion to 500 billion times less than Earth's atmospheric pressure at sea level. Such an atmosphere would be utterly impossible to breathe, a mere wisp against the vacuum. And while our own planet Earth has certainly demonstrated that complex ecosystems can flourish in the lightless, crushing depths of oceans, far removed from the sustaining embrace of sunlight, there could be a significant problem that prevents such a thriving, hidden life from happening on Ganymede. This is due to the sheer depth of Ganymede's ocean. It is so immense, so deep, that the water at its very bottom would likely be compressed back into a form of ice through sheer, unimaginable pressure. Imagine water, under such immense weight, succumbing to the pressure and reforming into a solid, even at relatively warm temperatures. Life in the deepest parts of our own oceans here on Earth can survive thanks to the minerals and heat ejected from geothermal vents, those oases of chemical energy. With such a thick layer of compressed ice potentially separating Ganymede's rocky core from its vast liquid ocean, it is currently considered unlikely that such direct geothermal activity, crucial for supplying raw chemical energy and nutrients, would occur there. Europa, Ganymede's neighboring moon, is, because of this, considered a more likely candidate for harboring life, as its ocean is thought to be in direct contact with its rocky mantle. However, the story of Ganymede's interior is far from settled, and there's a captivating twist. If Ganymede's ocean is salty, which there is an increasing, tantalizing amount of evidence for, it could drastically change our understanding of Ganymede's internal makeup. Models suggest that with a salty ocean, it could be that there are multiple layers within the moon, divided by sheets of different types of ice, perhaps even layers of hot ice that behave strangely under pressure. If this is indeed the case, the most internal liquid layer could, in fact, be in direct contact with the rocky core, an immense scientific leap that would significantly increase the chances of life existing there. Finding sustenance from geothermal vents, this quiet possibility whispers promises of hidden ecosystems waiting in the deep. But underneath Ganymede's vast blankets of ice and its immense hidden ocean exists something else, something truly surprising, something that, at present, scientists do not have a complete, satisfying explanation for, somehow, inexplicably, Ganymede is producing its own magnetic field. Imagine that for a moment. A moon, orbiting a giant planet, yet possessing its own independent magnetic shield, a feature we typically associate with planets that have dynamic, molten cores. The magnetic field of Ganymede was first discovered by scientists in 1996, a momentous revelation that occurred when the Galileo spacecraft began a series of daring flybys of this icy titan. The biggest, most compelling indicator of a magnetic field is the presence of auroras, those ethereal dancing lights in a planet's or moon's atmosphere. And incredibly, auroras were indeed detected in Ganymede's tenuous atmosphere, shimmering evidence of powerful magnetic forces at play. Not only that, but as the Hubble Space Telescope meticulously studied Ganymede over an extended period, an even stranger detail emerged: these auroras, unlike what might be expected from such a distant, complex system, didn't wobble as much as scientists had initially anticipated. This subtle yet significant stability is likely a result of something known as magnetic friction within a salty water ocean located deep under the surface. Imagine the currents within that hidden ocean interacting with magnetic fields, creating a subtle drag, a dampening effect that stabilizes the auroras above. A magnetic field is profoundly significant. On Earth, it is this very feature, our planet's invisible magnetic shield, that shelters us from the relentless, harmful solar radiation, enabling all life to flourish on our delicate surface. The magnetic field around Ganymede, however, does not offer complete protection from such harsh radiation. Being tucked deep within Jupiter's incredibly powerful magnetic field and its vast radiation belt means Ganymede's surface is still getting bombarded with a considerable amount of radiation. Ganymede's surface still experiences a dose of about 5 to 8 rem, an amount potent enough to make a human severely ill, or even dead, in just a mere 2 months. But even this level of protection, however incomplete, is still significantly better than what its closer orbiting neighbors, Io and Europa, endure. The profound puzzle, the great mystery that still captures the imaginations of scientists, is not just that Ganymede has a magnetic field, but why it has one at all. Our planet's core, for instance, is a swirling, churning cauldron of hot, molten iron. Convection currents within this liquid core actively move electrons, and it is this dynamic motion that generates the powerful magnetic field that so reliably surrounds and protects us here. However, by all conventional understanding, this process should simply not be happening on Ganymede. Ganymede is significantly smaller than Earth, and given its relatively smaller size and its presumed composition, a mix of rock and vast amounts of water, ice scientists believe that its core should have cooled down sufficiently by now. It should, theoretically, be a solid mass rather than a liquid, molten one. A solid core would fundamentally prevent electrons from moving through convection, and thus, it would prevent the generation of a magnetic field. And strikingly, none of Jupiter's other large moons possess a magnetic field. In fact, Ganymede stands alone, the only moon in our entire solar system that has its own magnetic field. So, what exactly is going on deep within its core? The answer, scientists whisper, is not yet known for sure, but the solution might lie in Ganymede's incredible, intricate relationship with its parent planet and its neighboring moons, and a powerful, unseen process known as tidal heating. Ganymede, in its majestic cosmic ballet, orbits around Jupiter roughly once every 7 Earth days. Its orbit is subtly eccentric, meaning that at some points in its journey, it comes slightly closer to Jupiter than at others. This constant, gentle variation in distance is crucial. When any celestial object comes under a strong gravitational force, it will experience a subtle stretching, an elongation in the direction of that force as its mass is pulled towards the source of gravity. However, as that object then moves further away from the gravitational source, it will gently compress back towards its original, more spherical shape. Because Ganymede follows this slightly eccentric orbit around Jupiter, it is constantly, rhythmically, coming under slightly more and then slightly less gravitational influence. This means it is perpetually stretching and contracting, an unseen internal kneading. Have you ever taken a piece of blue tack, that pliable, sticky substance, and repeatedly pulled and stretched it in your hands, perhaps then pushing it back into a ball shape? If you have, you might have noticed that after a while, it becomes surprisingly warm. This warmth is born from friction, as the material within rubs against itself. Now, imagine this phenomenon on a vastly grander scale, on the scale of moons and planets. This subtle yet constant stretching and contracting produces immense friction deep within Ganymede's interior, and this friction generates heat. A tidal force that creates heat through friction is precisely what we call tidal heating. It is a fundamental process in our solar system, shaping worlds in unseen ways. On top of this, in a process I find truly fascinating, Ganymede has formed an incredibly precise orbital resonance with two of its fellow Galilean moons, Io and Europa. This intricate gravitational ballet is known as a Laplace resonance. For every single time Ganymede completes one orbit around Jupiter, Europa will complete exactly 2 orbits, and Io, that fiery moon, will complete precisely 4 orbits. This mathematically precise, almost perfectly synchronized configuration has not happened by coincidence. It is profound evidence of the moon's gravities constantly pulling on each other, subtly influencing each other's paths. The entire system is attempting to conserve the resulting momentum. A cosmic dance governed by the immutable laws of physics. However, it means that Ganymede is constantly being tugged and pulled by the gravitational influence of its neighbors. It is perpetually under a lot of gravitational stress, subjected to this rhythmic external kneading. So, perhaps this relentless tidal heating, this internal friction generated by the moon's eccentric orbit and its synchronized dance with its siblings, is warming up Ganymede enough that its core remains in a liquid state after all. This would be the key, allowing it to continue to produce its powerful, enigmatic magnetic field. Scientists do not know for sure, of course, but it is a compelling hypothesis, one that would perhaps explain why the very surface of Ganymede is so remarkably interesting, bearing the scars and patterns of such immense hidden forces. You may have noticed, if you look closely at images of Ganymede's intricate surface, that it is distinctly split into large, dark regions and lighter regions. The darker areas cover about 1/3 of its total surface, while the lighter regions make up the remaining 2/3. Through careful examination of the number of impact craters on these 2 distinct sections, scientists have been able to deduce that the dark regions are, in fact, older than the lighter ones, as they contain a much higher concentration of craters, each one a silent testament to ancient bombardments. The lighter regions, while bearing fewer craters, are home to a remarkable network of long ridges and grooves, colossal geological features that can reach up to 700 meters high and extend for thousands of kilometers long. They are truly an impressive sight, etched across the face of this giant moon. But once again, the question lingers. Scientists are not entirely sure how these prominent ridges formed. One compelling explanation, however, returns us to the concept of those powerful tidal forces. Perhaps, during a particularly unstable period of Ganymede's ancient history, these tidal forces were so immense that they stretched out the moon's surface, tearing it apart and creating these vast, parallel scars. Could it be that this very same tidal force, this relentless kneading, was also responsible for warming Ganymede's core, preserving its liquid state, and allowing its magnetic field to persist across billions of years? The causal link is a tantalizing one, connecting the surface features we observe to the hidden workings of its core. Whatever its ultimate cause, the magnetosphere of Ganymede has been instrumental in helping scientists understand the very composition of the moon itself. By meticulously measuring the areas where auroras appeared in Ganymede's tenuous atmosphere, those dancing lights reflecting unseen forces, scientists were able to confirm, with striking certainty, the existence of Ganymede's subsurface oceans. Imagine that discerning the presence of a vast, hidden sea, deep beneath kilometers of ice, simply by observing the subtle glow of light in the moon's upper atmosphere. It is a profound testament to the ingenuity of scientific inquiry, allowing us to unveil the deep secrets of a world without ever having set foot there. And as for the rest of Ganymede's many mysteries, the whispers of its formation, the secrets of its grooves and ridges, perhaps the JUICE mission, the Jupiter Icy Moons Explorer, will provide us with the answers we seek. This ambitious spacecraft from the European Space Agency is set to launch in 2022, a long journey ahead, and though it won't reach orbit around Ganymede for another 10 years after that, its mission is specifically designed to investigate the inner workings of a number of Jupiter's moons, with a strong focus on Ganymede. Until then, perhaps we will have to allow Ganymede's many profound mysteries to remain just that, a mystery, a quiet invitation for future generations to explore and unravel the secrets of this colossal magnetic moon. We drift now, our cosmic vessel gently leaving the immense magnetic presence of Ganymede behind. As its grand form recedes into the starlit distance, we turn our gaze towards the final member of Jupiter's celebrated quartet of Galilean moons, Callisto. While the names Io, Europa, and Ganymede might spark immediate recognition, Callisto often lingers quietly in the shadow of its more famous siblings. Indeed, you might find yourself hard-pressed to recall many facts about it at all, a testament, perhaps, to its subtle nature. Does this signify a mundane, uninteresting world, or simply a realm about which we possess limited knowledge? On the contrary, dear friend, we actually know more than one might first assume, and Callisto is, in its own ancient, scarred way, far from boring. It holds a profound story, etched across its very surface. Let us begin by quietly placing Callisto within the grand tapestry of the Jovian system. Callisto holds the distinction of being the third largest moon in our entire solar system. An impressive stature indeed. In terms of sheer scale, it is just slightly smaller than the planet Mercury itself, measuring approximately 4,020 kilometers across. However, while its diameter is merely 58 kilometers less than Mercury's, Callisto possesses only about a third of the mass of that inner planet. This significant difference implies that Callisto is considerably less dense than Mercury, and consequently, its gravitational pull is far, far weaker. It is also the second largest of the Galilean moons by mass. Following Ganymede, Callisto orbits Jupiter at a much greater distance than its three inner siblings, a solitary sentinel at the periphery of the major Galilean dance. Its average distance from Jupiter is a remarkable 9 million kilometers, and it takes a more leisurely 17 Earth days to complete one orbit. Even at this substantial remove, however, Callisto remains tidally locked with Jupiter, faithfully presenting the same side, the same unchanging face, to its titanic parent planet, forever gazing inwards. This greater distance, however, carries a significant consequence. It means that Callisto is not locked in an orbital resonance with the other three Galilean moons. And, interestingly, we do not believe that it ever was. Its dance is its own. Apart from the synchronized ballet of Io Europa and Ganymede, Callisto, despite its distant, icy demeanor, does possess a very tenuous atmosphere, a faint breath clinging to its ancient surface. This wispy envelope is composed primarily of carbon dioxide, and there is also a possibility of oxygen, though oxygen itself has never actually been definitively detected. We know, however, that this atmosphere is so incredibly thin that the individual molecules contained within it do not frequently collide with one another. Theoretically, such a fragile atmosphere should be relentlessly stripped away by the harsh processes of atmospheric loss within a mere 4 years, vanishing into the vacuum of space. Yet, it persists. Scientists believe that Callisto's ancient crust is constantly replenishing these lost atmospheric particles through the process of sublimation of carbon dioxide ices from its surface. This continuous, subtle outgassing is evidenced by some interesting, almost ephemeral surface features, a quiet testament to a delicate balance between loss and renewal. Now, let us turn our gaze to the most defining characteristic of Callisto, its surface. The surface of Callisto is, quite remarkably, one of the most ancient in our entire solar system. Evidence meticulously gathered and analyzed places its formation at over 4 billion years old, a venerable chronicle etched in cosmic time. You will immediately notice the distinctive speckled nature of Callisto, its entire surface appearing as if it has been thoroughly peppered. Indeed, it is completely covered with impact craters of various sizes, more so than any other object we have observed in our solar system. In fact, its surface is so densely cratered that it is close to what scientists call saturation. This means that any new crater that forms will, in all likelihood, simply overlap another, erasing an older scar as it creates a new one. Without any significant geological activity, cratering is perhaps the only process that has profoundly and consistently impacted Callisto's appearance throughout its incredibly long lifetime. Why, then, is Callisto's surface so astonishingly old and so heavily cratered compared to a multitude of other celestial bodies in our solar system? The answer lies in its profound geological inactivity. On geologically active planets, like our own Earth, there are dynamic processes that can effectively erase almost all evidence of past impacts. Earth, for instance, possesses one of the least cratered surfaces in the solar system, precisely because so much happens on its vibrant surface. Our planet is alive with weather patterns, flowing water, diverse plant life, erupting volcanism, shifting tectonic plates, and indeed, human activity. All these forces conspire together to break apart, wear down, and uplift the ground, constantly refreshing and remaking our planet's face. Even other Jovian moons, like Europa or Io, possess comparatively fewer craters than Callisto. This is due to the intense tidal forces they experience from Jupiter, which instigate profound geological activity on their surfaces, ceaselessly resurfacing them. This, however, is not the case with Callisto. Callisto, crucially, shows no discernible signs of geological processes such as active volcanism or the grand dance of plate tectonics. And so, its ancient surface has remained largely intact, a frozen tableau, preserving its primordial scars through all these billions of years. The very limited tidal forces acting upon Callisto, and consequently, the profound absence of geological activity, impact Callisto in another deeply unique way. There are simply no mountains to speak of on its entire surface. When Callisto initially formed, in the very earliest, tumultuous beginnings of our solar system, it was likely an ocean world, brimming with liquid water. But over the eons, without the internal heating mechanisms of its siblings. That ocean has since frozen over entirely. And, apart from the relentless bombardment of meteors, it has largely stayed precisely the same ever since. A true fossil world, a living museum of the early solar system. So, let us now take a closer look at some of these remarkable craters. For some of the largest are truly impressive, monumental structures, cosmic works of art, crafted by immense impacts. This, for instance, is Asgard, the second largest impact crater on Callisto, a colossal depression measuring a staggering 1,600 kilometers in diameter. And then there is Valhalla, a name that evokes ancient sagas, and rightly so, for it is the largest multi-ring impact crater in the entire solar system, boasting an incredible diameter of 3,800 kilometers. These very craters contribute significantly to the unique, almost mesmerizing appearance of Callisto, as they contain more concentric rings than any other craters found anywhere else we know. With these truly gigantic craters, the impactor, the celestial body that struck Callisto, was so immense and powerful that it may have completely punctured the moon's relatively thin crust. The material then flowed and eventually refroze, creating the lighter patches you often see in their centers. Smooth plains of new ice. Zooming in even further on these central regions, you'll notice they often have a mottled appearance, a striking contrast between brighter, knob-like features and a darker, smoother plane. There seems to be a significant difference in contrast here. These mottled regions are also considerably less cratered than the rest of Callisto's ancient surface, which would make perfect sense if the smooth plains truly represent a refrozen surface, likely making them around 2 billion years younger than the surrounding, more heavily cratered terrain. The multiple rings, those concentric circles radiating outwards, are likely fractures in the crust, a concentric failure of the brittle shell of the moon as the immense shock wave propagated outwards. Interestingly, however, even within these rings, those bright knobs are still visibly present. So, what precisely are these mysterious knobs? Well, they are believed to be the degraded remains of the millions of older crater rims from Callisto's deep, ancient past. We don't know exactly why they have degraded so extensively over time, but perhaps it is due to constant bombardment by micrometeor impacts, or simply the slow, gentle sublimation of the ice over eons, gradually wearing them down. They appear brighter than the lower planes because the rocky debris, those darker materials from the meteors and micrometeors, will have slowly fallen down the slopes of these knobs over time, leaving the purer, more reflective ice exposed at their tops. Smaller impact craters on Callisto are also fascinating due to their unique characteristics. Most impact craters on Callisto appear shallower compared to those on our own moon, for instance, even for comparable sizes. Take the Lewin impact structure. It's well over 100 kilometers wide, yet it's only about 600 meters deep. This remarkable shallowness could be because the impactor itself was breaking apart before it impacted, causing more of a spread-out, shotgun-like effect on the surface, or it could be that the surface has since been subtly leveled off by the immense shock waves from other, larger nearby impacts that occurred later. This particular crater is believed to be over 1 billion years old at least, yet you can still clearly discern the ejecta that streamed away from the impact point, clear, visible evidence of how astonishingly unchanging this remarkable moon truly is. With some craters, like our crater, there is even a distinct large dome found in the middle. This contrasts with typical large impacts on other worlds, where you usually see a few concentric rings and a raised peak in the center, as is very much the case on our moon. However, Callisto also presents some truly remarkable examples of large craters where just the opposite occurs. Look at Tinder here. Instead of a central peak, there is actually a pit in the center. Why does Callisto possess such unique craters? It could be due to the fundamental nature of Callisto's crust. It is not just brittle, but also relatively thin, with either soft ice or a salty ocean beneath. Estimates place the crust's thickness at a range of 80 to 150 kilometers. The Galileo space probe, which spent several years gracefully orbiting Jupiter, dedicated a significant portion of its invaluable time to aptly studying the Galilean moons. During its observations, Galileo made a crucial discovery concerning Callisto. It found that Jupiter's immense magnetic field could not penetrate through Callisto. This profound observation implied the existence of a highly conductive layer under the surface, at least 10 kilometers thick. This phenomenon could not have occurred in solid ice or silicates alone, unless the ice layer is at least partially molten, or very large temperature gradients can be maintained below the ice to create a conductive effect. Further data also suggests that Callisto has a small silicate core at its very center, with a radius of about 600 kilometers. This naturally leads us to a profound and intriguing question. Can Callisto, with its potential for a subsurface conductive layer, or even an ocean, truly be conducive to life, much like other icy worlds thought to possess water mantles under their surfaces? Well, life as we know it fundamentally requires liquid water and a source of energy to exist. Callisto might indeed possess an ocean of liquid water beneath its ancient surface. However, being approximately 800 million kilometers away from the Sun, it receives barely any heat from our distant star, and critically, the profound absence of significant tidal forces from Jupiter, unlike its inner siblings, means there is no continuous internal kneading to generate substantial heat. This leaves radioactive elements within its core as the only potential source of heat to warm this subsurface ocean, if it truly exists. And unfortunately, even a direct visit to Callisto might not definitively prove anything regarding habitability. Moons like Europa and Enceladus tantalize us with visible vents ejecting water directly from their subsurface oceans, meaning we can investigate their habitability prospects without ever having to venture into the oceans themselves. No such vents have been observed on Callisto, meaning scientists would have to penetrate its thick crust in order to discover these crucial details. All these factors combined, unfortunately, lead scientists to believe that the environmental conditions necessary for life appear to be less favorable on Callisto than on any of the other icy worlds we are currently studying. Nevertheless, Callisto, despite its perceived lack of biological promise, should by no means be ignored. If humanity ever truly embarks on the grand endeavor of exploring the outer solar system in a sustained manner, Callisto could prove to be a perfect base of operations. You see, orbiting at a significant distance of 1.9 million kilometers from Jupiter, Callisto is uniquely located beyond Jupiter's main, intense radiation belt. This means its environment is thousands of times more conducive to human exploration and long-term habitation than its inner, more irradiated moons. Furthermore, Callisto possesses an abundance of water ice, a crucial resource that can be utilized not only for propellant production, fueling our future deep space missions, but also, of course, as the staple to keep humans alive. The process of separating hydrogen from oxygen in water ice also conveniently leaves us with breathable oxygen, a vital resource for any future outpost. Callisto's profound geological stability, its unchanging, ancient surface, would make for building structures on its surface relatively worry-free, without the constant threat of seismic activity or volcanic eruptions. And the remarkable lack of huge mountains or deep trenches across its entire surface means it would be faster, easier, and significantly more efficient to travel over, facilitating surface exploration and infrastructure development. From Callisto, a strategically located outpost, we could more safely and effectively explore the inner Jovian system from a comfortable, safe distance, observing its turbulent dynamics. Or it could serve as a vital way station, a cosmic stepping stone, for heading even further into the enigmatic outer solar system. Lifting off from Callisto would also be ideal, thanks to its relatively low gravity, making launches less energy intensive. And, once in orbit, one could even utilize a gravity assist from a close flyby of Jupiter, slinging oneself further into the cosmos. While it is true that this remains a futuristic prospect, a vision for generations yet to come, if we ever do evolve into a truly spacefaring species, establishing a base on Callisto is a distinct and highly practical possibility. Now, while Galileo, that brave probe, did an admirable job studying Callisto during its few close flybys, there are still many information gaps that need to be filled. Its ancient surface, its hidden depths, still hold many secrets. With any luck, we will begin to bridge those gaps to receive more answers from the European Space Agency's Jupiter Icy Moon Explorer. JUICE. This mission, as we have discussed, is due to launch in 2022, and it is projected to reach the Jovian system by 2030. JUICE will explore Jupiter and three of its largest moons, Ganymede, Callisto, and Europa. ESA has meticulously planned several close flybys of Callisto during this mission, specifically designed to delve deeper into its mysteries. This mission might provide crucial new insight into questions like, does it truly have a subsurface ocean? And if so, does it or can it sustain life beyond those profound questions? There are also the questions we haven't even thought to ask yet, the unexpected revelations that await us. Who knows what more we will still discover about this incredible ancient moon, this quiet chronicler of the early solar system. Having journeyed through the dynamic, awe-inspiring family of Jupiter's Galilean moons, allowing our minds to float gently over Io's fiery heart, Europa's hidden ocean, Ganymede's magnetic enigma, and Callisto's ancient, cratered face, we now prepare to shift our cosmic vantage point. Our focus, subtle as a whisper carried on the solar wind, turns towards another ring giant, the elegant jewel of our outer solar system, Saturn, and within its celestial embrace lies a world of ice and profound mystery, a moon that often escapes the popular imagination, yet holds secrets as deep and compelling as any we have encountered. This is Rhea, Saturn's second largest moon, while you are far more likely to have heard the resounding name of its colossal sibling, Titan. With its thick, hazy atmosphere, Rhea is, in its own quiet right, a truly fascinating place, harboring many wonders and profound enigmas that beckon our gentle curiosity. Imagine, if you will, vast ice cliffs, hundreds of meters high, carving ethereal pathways across its frozen surface. Envision an internal structure that quietly defies many of our established scientific models, challenging the very frameworks we use to understand celestial bodies. And then consider an enigmatic discovery that lingers around this moon, a revelation as strange and captivating as the very thing we did not find, a profound absence that speaks volumes. It is time now for this often overlooked moon to step out, if only for a moment, from the immense shadow cast by its larger, more famous sibling. Let us learn all there is to know about Rhea. I am Alex Mullen, and you are quietly watching Astronomy. Join me today on a serene voyage of discovery, a gentle drifting into the Saturnian system, and to the moon Rhea. We will seek to understand what patient scientists, through decades of observation and the remarkable journeys of our robotic probes, have gently uncovered there. We will witness, through the eyes of our distant voyagers, its subtle, profound beauty for ourselves. Our story of Rhea begins in the cold, distant reaches of space, but its discovery echoes with human ingenuity and dedication. Rhea was first glimpsed and documented on the 23rd of December in the year 1672 by Giovanni Domenico Cassini, this brilliant Italian astronomer whose name is now deeply woven into the fabric of space exploration, made numerous, invaluable contributions to our understanding of Saturn and its intricate family of moons. Rhea itself was named after the Titan goddess Rhea from ancient Greek mythology, a fitting celestial tribute. For centuries, since its initial discovery, this quiet moon has been a subject of fascination, a beacon of subtle intrigue for astronomers and planetary scientists alike, waiting for its secrets to be slowly unveiled. Let us begin with the basics, those fundamental strokes that paint Rhea's cosmic portrait. Rhea holds its place as the second largest moon of Saturn, outshined only by the mammoth presence of Titan, that unique world with its dense atmosphere. Rhea possesses a significant diameter of 1,528 kilometers. To help us truly grasp its scale, let us imagine it here on Earth if we were to gently place Rhea next to our own planet. Its vast expanse would stretch approximately the distance from the bustling heart of London all the way to the historic city of Warsaw, a truly immense sphere. Rhea orbits Saturn at a graceful distance of about 527,000 kilometers, completing one full orbit every 4.5 Earth days, and, like many other large moons throughout our solar system, it is locked in a synchronous rotation with Saturn, meaning that the same side, the same unchanging face, perpetually gazes towards the ringed planet. This synchronized ballet, a common feature among large celestial companions, is a testament to the immense gravitational influence exerted by a massive parent body. The surface of Rhea is a spectacle of subtle brilliance, one of the most reflective in our entire solar system. It possesses a remarkable albedo of 0.7. What does this mean? In our quiet contemplation, it means that Rhea reflects an astonishing 70% of the sunlight that gently falls upon its surface. This makes it appear a brilliant, almost blinding white against the deep, inky backdrop of space, a luminous beacon in the cold vastness. This exceptionally high reflectivity is a direct consequence of its composition. Rhea's surface is primarily composed of water ice, pure and unblemished. But this does not, as one might perhaps assume, render it a featureless, monotonous sheet of ice. Far from it. This moon is, in fact, heavily cratered, its surface a vast, ancient parchment telling a profound story of countless impacts, a long, violent, yet ultimately enduring history written in its very scars. The largest and most striking of these ancient craters, aptly named Mamaldi, spans an impressive 480 kilometers in diameter, a distance comparable to that from the historical heart of Paris to the vibrant city of Amsterdam. These craters are not merely blemishes on Rhea's pristine surface. They are, in essence, windows into the moon's deep past, providing invaluable clues about its composition and the relentless cosmic processes that have shaped it over billions of years. Observations from our distant probes have even shown that the bottoms of some craters appear subtly darker than the surrounding, brilliant terrain. This intriguing contrast could indicate that the immense force of the impacts has excavated material from beneath Rhea's bright, reflective surface, possibly exposing darker, amorphous forms of water ice, or perhaps even impact melt, residues of the ancient collisions that forever scarred its face. But one of the most intriguing and visually captivating features on Rhea, one that whispers of a more dynamic past, is its intricate system of bright, wispy streaks that crisscross its surface. These enigmatic patterns were first observed in stunning detail by the Voyager space probes in the early 1980s, tantalizing glimpses that hinted at a deeper story. However, their true nature, their profound geological origin, remained shrouded in mystery until the Cassini mission arrived decades later. providing us with high-resolution images that peeled back the layers of uncertainty. Initially, these wisps were thought to be mere deposits of frost or perhaps thin layers of ice, a delicate overlay on Rhea's ancient face. But Cassini's keen eye, its unparalleled clarity, revealed a far more dramatic truth. These wisps were, in fact, ice cliffs, towering geological features, some reaching hundreds of meters high. They are likely the direct result of tectonic activity in Rhea's deep past, a time when the icy crust experienced profound stress, fracturing and allowing some sections to be thrust upward, creating these grand, linear escarpments. These majestic features, these silent, frozen walls, offer us invaluable clues about the moon's geological history and the powerful, unseen processes that have meticulously shaped its surface over billions of years, transforming a simple ball of ice into a world of complex, subtle beauty. But Rhea's many mysteries do not simply end at its surface. They delve deeper into the very heart of its being. In 2010, data meticulously collected by the Cassini spacecraft led to a truly surprising announcement, a whisper from the depths of space that redefined our understanding of this quiet moon. Rhea, it appeared, possessed a tenuous atmosphere, or exosphere. While a small amount of gas around Rhea might have been expected due to various subtle processes, it was entirely unexpected that there would be enough to be genuinely measurable, a detectable breath clinging to its icy form. The detected atmosphere consisted primarily of oxygen and carbon dioxide, and while incredibly thin, with the oxygen being about 5 trillion times less dense than Earth's atmosphere at sea level, its mere presence raised intriguing questions about its origin and its ability to persist. One prevailing theory, a gentle hypothesis in the vastness of the cosmos, suggests that the oxygen within this exosphere is produced through a process called radiolysis. This occurs when the water ice on Rhea's surface is struck by energetic ions streaming from Saturn's powerful magnetosphere, causing the water molecules to break apart and release free oxygen. The carbon dioxide, on the other hand, is thought to be the result of complex organic molecules present on the surface being gently oxidized by the very oxygen now in the exosphere, a subtle chemical dance in the cold. This remarkable discovery elevated Rhea to a unique status. It became the first moon known to possess an oxygen atmosphere, a distinction previously only held by Jupiter's much larger moons, Ganymede and Europa. It quietly opened up vast new avenues for scientific research, prompting deeper contemplation into the complex, intricate interactions between Saturn's family of moons and the planet's immense, powerful magnetosphere, an invisible hand shaping their very existence. Rhea's exterior, with its ancient craters and towering ice cliffs, is undeniably fascinating. But what of its interior? Let us dive deeper, literally, into the unseen heart of this moon. While we lack the ability to directly observe what truly lies beneath Rhea's vast, icy surface, dedicated scientists have employed various ingenious methods to infer its internal structure. Based on Rhea's average density, which is a mere 1.236 grams per cubic centimeter, only slightly higher than that of water, we can confidently deduce that Rhea is composed primarily of water ice, making up about 75% of its total mass, with a smaller fraction of rocks, comprising the remaining 25%. Because of this composition, Rhea has often been affectionately described as a frozen, dirty snowball, a colloquial yet accurate representation of its icy, rocky mix. This composition places Rhea in stark contrast to moons like our own, which are predominantly dense, rocky bodies, solid spheres of stone and metal. When the Cassini spacecraft, that tireless explorer, visited Rhea, its sophisticated instruments provided invaluable data about Rhea's composition. spectroscopic observations, which analyze the light reflected from its surface, definitively confirm that water ice is indeed the dominant component of Rhea's outermost layer. But a surprising discovery also emerged: the detection of carbon dioxide trapped within the surface ice. This intriguing finding suggests that Rhea's ice is not simply pure water. It contains other compounds, possibly including complex organic molecules, subtly mixed within its frozen matrix. This raises quiet questions about the moon's deeper chemistry. Due to its higher moment of inertia, a measurement that tells us how mass is distributed within a rotating body, most scientists currently believe that Rhea is not differentiated into distinct layers. Instead, it is thought to be a relatively homogeneous mix throughout, a uniform blend of ice and rock, with the sole exception of a small, likely rocky core at its center. This model paints a picture of a world that never fully separated into distinct geological strata, unlike the layered Earth. However, this idea has faced challenges. In 2006, a paper published in the esteemed journal Icarus suggested a counter-hypothesis that Rhea might, in fact, harbor a layer of liquid water beneath its surface, a hidden subsurface ocean. While this concept remains highly speculative and is certainly not as strongly supported as the evidence for subsurface oceans on more active moons like Europa or Enceladus, it is nonetheless an intriguing possibility. Such a hidden ocean, if it truly exists, would have significant implications for Rhea's potential habitability and for our broader understanding of the conditions necessary for liquid water to persist in the frigid, distant outer solar system. Rhea's interior holds its own mysteries, certainly, but one of the most puzzling and subtle features of Rhea is its very shape. While many large moons and planets, under the immense influence of their own gravity, tend towards a near-perfect sphere, Rhea is noticeably non-spherical. It is slightly flattened at its poles and gently bulges at its equator, a shape that planetary scientists call a triaxial ellipsoid. What makes this particularly strange is that Rhea's observed shape doesn't quite match what we would precisely expect based on its rate of rotation. This subtle discrepancy, this slight deviation from theoretical prediction, has led scientists to propose that Rhea might possess a non-uniform internal structure, suggesting that denser material is perhaps concentrated in certain areas away from its very center. Imagine an uneven distribution of mass within its core, subtly pulling and pushing against the perfect symmetry we might anticipate. This hints at a complex, perhaps even turbulent, internal history that has left its subtle, lasting mark on Rhea's outward form. Now, let's turn our attention to one of the most exciting and transformative moments in Rhea's recent exploratory history: the Cassini mission's close flybys. The Cassini spacecraft, a monumental joint project conceived and executed by NASA, ESA, and the Italian Space Agency, spent over a decade meticulously studying the intricate Saturnian system. During its long and fruitful tenure, it conducted several thrilling, close encounters with Rhea, literally brushing past the moon to gather invaluable data. The closest of these daring flybys occurred on the 11th of January, 2011, a breathtaking moment when Cassini passed a mere 76 kilometers above Rhea's frozen surface. The very last close flyby took place on the 9th of March, 2013, with Cassini passing just 997 kilometers above Rhea's shimmering surface. These incredibly close approaches were invaluable, allowing the spacecraft to capture unbelievably detailed images of Rhea's heavily cratered terrain and to gather crucial, nuanced data about the moon's precise composition. These close encounters also allowed scientists to confirm, definitively, that Rhea does not possess an internal magnetic field, unlike Ganymede. These flybys provided us with our very best, most intimate look yet at Rhea's intricate surface features. They meticulously imaged a landscape dominated by two distinct types of terrain: heavily cratered regions and younger, smoother plains. the heavily cratered areas, first hinted at in the earlier Voyager missions, are thought to be incredibly ancient, possibly dating back to the very earliest days of our solar system's tumultuous formation. These primordial surfaces, pockmarked by countless impacts, offer a profound geological record of the intense bombardment that characterized the solar system's youth, a time when debris was far more abundant and violent collisions were common. The smoother plains, on the other hand, are likely the direct result of a more recent resurfacing event, such as the widespread deposition of material ejected from truly massive impact events. This ejected material, cast across the surface, would have subsequently fallen back down, gently filling in older craters and effectively creating these smoother, more uniform regions, a testament to the moon's ongoing, albeit subtle, geological evolution. But perhaps one of the most intriguing and subtle results from the extensive Cassini mission was not what it found, but rather what it didn't find. Prior to Cassini's arrival in the Saturnian system, some scientists had proposed a captivating hypothesis that Rhea might actually possess a system of rings, similar in concept to those of Saturn, though far more tenuous. This intriguing idea was based on some unusual measurements of electron densities detected around Rhea by Cassini in 2005, which seemed to hint at the presence of a delicate, dusty ring. However, despite careful and exhaustive searches conducted during its close flybys, Cassini ultimately found no direct evidence of rings around Rhea. This non-detection doesn't completely rule out the theoretical possibility of some kind of extremely diffuse debris disk surrounding Rhea, perhaps too faint or temporary to be conclusively detected. But it does make the existence of such a ring system much less likely, leaving that particular mystery as a tantalizing, unresolved question in the silent expanse of space. Rhea's position within Saturn's vast and complex system of moons also lends it a unique characteristic. Rhea orbits Saturn within what is known as the E-ring, a highly diffused, almost ethereal ring composed of countless tiny ice particles. These ice particles are widely thought to be continuously supplied by the spectacular cryovolcanic eruptions from its smaller, far more active neighbor, Enceladus, while Rhea itself does not appear to be geologically active in the dramatic, geyser-like fashion of Enceladus. Its precise position within this E-ring means that it is constantly interacting, however subtly, with these myriad ice particles. Although Rhea resides in the very extremities of the E-ring, beyond where it is most dense, this long-term interaction over the vast expanse of cosmic time could subtly affect Rhea's surface properties and even contribute to the moon's remarkably bright, reflective appearance. It's a quiet, ongoing dance, a testament to the subtle interconnectedness of worlds within a planetary system. As we gently reflect on all that we have learned about Rhea, it becomes clear that this moon, often quietly overshadowed by its more famous and outwardly dramatic siblings, is truly a fascinating world in its own right, from its ancient, heavily cratered hemisphere to its younger, subtly smoother side, from its tenuous, almost imperceptible atmosphere to its unique place within Saturn's complex and intricate system of moons and rings. Rhea continues to intrigue scientists and spark our imagination, a quiet, luminous beacon in the cold. But our exploration of Rhea, like so many cosmic journeys, is far from over. Many profound questions quietly remain unanswered. What is the exact, precise nature of its interior structure? How has it evolved over the billions of years since its ancient formation? Could it, by some unforeseen cosmic twist, harbor simple forms of life within that hypothetical, deeply buried subsurface ocean? These questions, and many more yet to be formulated, patiently await the arrival of future missions to the Saturnian system, probes designed to peel back the remaining layers of its quiet mystery. While there are currently no specifically planned missions whose primary target is Rhea, this captivating moon is highly likely to be observed and further studied by any future spacecraft sent to meticulously explore Saturn and its remarkable family of moons. As Rhea, with its ancient, ice-scarred face and its subtle, puzzling mysteries, gently recedes behind us, our cosmic journey carries us onward, deeper into the embrace of the Saturnian system, and here, awaiting our quiet contemplation, is a world that has captivated the imaginations of scientists and dreamers alike, a truly remarkable celestial body that stands as a unique jewel in our solar system's vast collection of moons. This is Titan, Saturn's biggest sibling, a realm of such profound distinction that it almost feels like a planet in its own right. While Rhea holds its quiet dignity, Titan commands attention, for it is the only moon in our entire solar system with a substantial atmosphere, a thick, hazy blanket that shrouds its surface in an eternal twilight. Furthermore, there is clear evidence of stable bodies of surface liquid upon its enigmatic face, a phenomenon previously thought to be unique to our own Earth, and perhaps most thrilling of all, to truly bridge the immense distance between us, mankind has actually visited it, sending a brave robotic emissary to touch its alien soil. Because of this, I will be able to share with you many real photos and even glimpses of video footage, bringing this distant world closer to your quiet gaze. I am Alex Mullen, and you are peacefully watching Astrum. In this quiet space, let us unravel everything you could ever wish to know about Saturn's biggest moon, Titan. Our story of Titan begins, as all good stories do, with setting the scene, providing a little context to this truly remarkable planet-like place. Titan is the sixth spherical moon from Saturn, one of the grand collection that orbits the ringed giant. And unlike Jupiter's majestic quartet of Galilean moons, where large companions dance in close proximity in the Saturn system, Titan stands in solitary grandeur in terms of its immense size. The rest of Saturn's moons, while numerous and fascinating in their own ways, are simply tiny in comparison, mere pebbles next to Titan's colossal presence, to offer a sense of just how truly big it is. Imagine this Titan's diameter is an impressive 50% larger than that of Earth's own moon, that familiar silvery orb in our night sky, and it is a remarkable 80% more massive. Indeed, Titan holds the distinction of being the second largest moon in the entire solar system, surpassed only by Jupiter's colossal moon, Ganymede. Interestingly, Titan does actually appear slightly bigger than Ganymede if you were to place them directly side by side in your mind's eye. A curious optical illusion, but this apparent larger size is caused by Titan's extraordinarily thick atmosphere, that dense, hazy blanket that extends for hundreds of kilometers into space, effectively stretching its apparent diameter. Even so, Titan's true, solid diameter is still larger than that of the smallest planet, Mercury. Yet, it possesses only about 40% of Mercury's mass, a profound difference that speaks volumes about its fundamental composition. Its density is quite low for its immense volume, a crucial clue to what lies beneath its shrouded surface. Due to Titan's remarkably low density, it is widely believed that its composition is approximately half water ice and half rocky material. This stands in contrast to denser, rockier bodies. And unlike other celestial objects of this immense size that we have studied, it is believed Titan possesses a differentiated interior. This means it is structured in layers, much like an onion, rather than being a homogeneous mix, and, profoundly, like a number of other large moons in our solar system, one of those hidden layers is thought to be a liquid ocean, a vast, subterranean sea comprised of water and ammonia, nestled deep beneath the moon's crust. This hidden liquid ocean is, in a profound sense, comparable to Earth's own magma layer, situated between our planet's core and its outer crust. It has been maintained in a liquid state due to a delicate interplay of heat, immense pressure, and to a certain degree, the relentless tidal forces exerted by Saturn. The very existence of this hidden liquid layer was made even more likely, essentially proven, when Cassini, the intrepid spacecraft orbiting Saturn, made a remarkable discovery. It detected extremely low-frequency radio waves within Titan's atmosphere, subtle whispers of cosmic energy. Why was this significant? Because Titan's surface, as we understand it, is not known to be a particularly good reflector of such low-frequency radio waves. However, a deep, electrically conductive liquid interior, like an ocean of salty water, would be an excellent reflector, causing these waves to bounce back in a distinctive manner. Another compelling piece of evidence supporting this hidden ocean is a subtle yet profound observation. The surface features on the Moon have mysteriously shifted by up to 30 kilometers since Cassini began its meticulous observations. This implies that the surface, that outer crust we observe, is not rigidly attached to the Moon's core. Instead, it strongly suggests that it is floating on this deep liquid ocean layer, moving independently, a silent testament to the vast sea beneath. And while there is, as yet, no direct, irrefutable evidence of life existing on Titan itself, scientists do quietly speculate that the conditions within this very subsurface ocean would be precisely right for life as we understand it to exist. Imagine the possibilities: a liquid environment, shielded from the harsh surface conditions, potentially warmed by internal processes. Unfortunately, if life were to be found there, or indeed on the surface, we will have to wait a considerable while. There are currently no planned missions specifically designed to check out this tantalizing possibility. For the foreseeable future, Jupiter's moon Europa, with its closer proximity and seemingly more accessible plumes, is considered a more likely candidate for life investigation. It's a matter of scientific prioritization and logistical feasibility. Despite its differentiated interior, Titan does not, interestingly, produce its own magnetic field. However, Titan is still quite well protected from the harsh solar wind, that relentless stream of charged particles from our sun. This is because an impressive 95% of its vast orbit around Saturn occurs within Saturn's own immense magnetosphere, its protective magnetic bubble. This offers a vital, invisible shield, allowing Titan to exist in a relatively stable magnetic environment. Titan, in its stately cosmic dance, completes one orbit around Saturn approximately every 15 days and 22 hours. Its orbit is notably eccentric, meaning that its path around Saturn isn't perfectly circular. It's a slightly elongated ellipse. Furthermore, its orbital plane is also at a significant angle relative to Saturn's equatorial plane. These characteristics might lead one to suspect that Titan is a captured object, a rogue wanderer drawn into Saturn's gravitational embrace, much like some of Jupiter's irregular moons or even Neptune's Triton. However, this is likely not the case. Rather, like Jupiter's Galilean moons, it is thought that Saturn also once possessed several other large moons in its tumultuous youth, but most of these, tragically, are believed to have been destroyed through colossal collisions, immense cosmic crashes that reshaped the early Saturnian system. Titan, in this scenario, emerged as the lone victor, the solitary survivor of this violent, chaotic beginning. Titan's day, the time it takes for the moon to complete one rotation on its axis, is, like the day on our own moon, identical in length to its orbital period. This signifies that Titan's rotation is tidally locked to Saturn, meaning it forever presents only one face to its parent planet, an eternal, unwavering gaze. Not that this makes any visual difference to an external observer. However, Titan's omnipresent, thick, hazy atmosphere completely and utterly blocks any view of the surface from an outside perspective. One cannot see its features from afar. On the other hand, if you were to stand on Titan's surface, you might just be able to catch a glimpse of Saturn, though the view would be significantly obscured by that very same haze. A distant, muffled giant. This tidally locked state also means that if you were to stand firmly on one spot on Titan's surface, Saturn would never move in the sky, a fixed point of immense presence, an unmoving, veiled monarch. However, were one to magically remove Titan's pervasive haze, to peel back that thick atmospheric blanket, this is what the clear, unadorned view would truly look like, revealing a landscape shaped by unseen forces and covered in liquid. This brings us, quite naturally, to one of the most compelling and defining topics that truly sets Titan apart from every other moon in our entire solar system, its substantial atmosphere. I vividly remember the first time I ever saw a photograph of Titan. I was truly blown away, utterly captivated. It had never, not once, occurred to my young self that a moon could even possess an atmosphere. I imagined them all as airless, barren rocks. I thought, perhaps, it must have been a new planet they had recently discovered, or something equally grand. To my young eyes, what looked odd, truly strange, about this atmosphere was how incredibly far it stretched into space. When you see a picture of Earth, you notice that our atmosphere hugs the planet quite tightly, a delicate blue film. Titan, on the other hand, appears to be enveloped in a thick, almost suffocating blanket that seems to extend endlessly outwards. There are a number of profound reasons for this striking visual difference. The first is simply that, while Titan is considerably smaller than Earth in terms of its solid body, its atmosphere is an astonishing 1.9 times more massive than Earth's own atmosphere. To put that into perspective, on a per-surface area basis, Titan's atmosphere is a staggering 7.3 times more massive than ours. The second reason lies in Titan's gravity. It is significantly weaker than Earth's, meaning it doesn't pull its atmospheric gases downwards as strongly. This combination of immense mass and weaker gravity means that the pressure at Titan's surface is a remarkable 1.45 atmospheres, or 45% more than the atmospheric surface pressure here on Earth. And when comparing the two, you can truly visualize the immense extent to which Titan's atmosphere stretches into space. Its mesosphere, that upper layer, reaches a staggering 600 kilometers high. Earth's mesosphere, in stark contrast, stops at a mere 120 kilometers. So dense and extensive is this atmospheric envelope that even at a considerable distance of 975 kilometers, the Cassini spacecraft had to make subtle adjustments to its trajectory, fighting against the atmospheric drag to maintain a stable orbit when it made its closest approaches. Furthermore, like the planet Venus, Titan is what scientists call a super-rotator. This fascinating phenomenon means that its atmosphere rotates significantly faster than the solid body of the planet itself. This is particularly evident at the poles of the moon, where each pole harbors a distinct polar vortex. These immense atmospheric structures rotate once every 9 hours, a dizzying speed when compared to the moon's actual rotation period of 16 days. Imagine these polar vortexes as colossal, permanent hurricanes, ceaselessly churning and swirling in Titan's upper atmosphere, a testament to its dynamic and complex atmospheric circulation. So, what exactly does this mysterious atmosphere consist of, and why does it possess that distinctive orange hue? Well, the atmosphere is overwhelmingly composed of nitrogen, making up a remarkable 98.4% of its total composition, much like Earth's own atmosphere. The remainder is mainly methane, with small, trace amounts of hydrogen. But there's a crucial, colorful detail. There are also trace amounts of various hydrocarbons. These hydrocarbons are formed from the ceaseless breakup of methane molecules in the upper atmosphere, a process initiated by the energetic ultraviolet light from the sun. And it is these very hydrocarbons, these complex organic compounds suspended in the atmosphere, that are thought to impart Titan with its characteristic hazy orange hue, painting its very sky. This constant breakup of methane into hydrocarbons presents a profound puzzle. If methane were not continuously replenished, the moon would have run out of it within a mere 50 million years, a blink of an eye compared to the billions of years that mark the age of our solar system. This inescapable truth means there must be an active source that tirelessly replenishes the atmospheric methane. The most likely candidate for this replenishment is cryovolcanism, those enigmatic icy volcanoes we've seen on other moons, spewing forth not molten rock, but cold, liquid mixtures of water and methane from deep within Titan's interior. Interestingly, the possibility of biological life producing methane, though highly speculative, has not been entirely ruled out, leaving a tantalizing, if distant, whisper of possibility. The methane in Titan's atmosphere creates a significant greenhouse effect, trapping heat and warming the moon. Without it, the temperature on Titan would be considerably lower, plummeting even further into the frigid depths of space. Conversely, however, the pervasive haze, that thick blanket of hydrocarbons, also reflects a substantial amount of the incoming sunlight back into space, creating an anti-greenhouse effect. This delicate balance, this push and pull of warming and cooling, cancels out a portion of the potential greenhouse warming from the methane. Now, consider the sunlight itself. While Titan's upper atmosphere receives only about 1% of the sunlight that graces Earth, due to Titan's immense distance from the sun, another profound result of this atmospheric reflection is that the surface of Titan, deep beneath the haze, only receives a mere 0.1% of that already faint sunlight. Imagine the perpetual twilight. The brave Huygens team, who designed the lander, likened the immense difficulty of taking photographs at this incredibly low light level to attempting to capture pictures of an asphalt parking lot at dusk, a profound analogy for the perpetual gloom. All these factors combined mean that while it would indeed be remarkably dark, a human standing on the surface of Titan would only require an oxygen mask to breathe its alien air and to wrap up extremely warmly to be comfortable. It truly is bitterly cold on Titan, averaging a staggering minus 180 degrees Celsius. This means that any water present on Titan remains perpetually solid, an unbreakable, enduring ice, never melting, evaporating, or subliming into the atmosphere. Why, then, are there sometimes clouds on Titan? This is where the story truly becomes alien and fascinating. These are not water ice clouds, as we know them, but rather methane clouds. And this means, astonishingly, that yes, it can rain methane on Titan. In fact, the average temperature on Titan, that minus 180 degrees Celsius, is precisely right for methane to exist in a liquid state. Methane freezes at approximately minus 182.5 degrees Celsius and boils at minus 161.5 degrees Celsius. This narrow, unique temperature window, combined with the atmospheric surface pressure, immediately ignited the imaginations of scientists, filling them with immense excitement at the prospect of there being actual hydrocarbon lakes or seas on the surface of Titan, vast bodies of liquid similar to the water lakes and seas we cherish here on Earth. If there truly were such lakes on this distant moon, it would mark the very first time this phenomenon had ever been observed anywhere else in our solar system outside of Earth. This tantalizing possibility was, in fact, one of the main driving forces behind the ambitious Cassini-Huygens mission, an insatiable desire to see what truly lay beneath that thick, enigmatic atmosphere. The Huygens probe, named after Christian Huygens, the astronomer who discovered Titan in 1655, was meticulously designed to enter Titan's atmosphere and ultimately land on its shrouded surface. The remote possibility of even landing directly onto an alien ocean was carefully taken into account during its intricate design process, a testament to the scientific foresight. As the probe gently descended, its parachute billowing softly in the alien winds, and after an almost 3-hour-long, nail-biting journey through the dense atmosphere, it finally came to rest on the solid surface of Titan. Sadly, it wasn't able to see any active, expansive lakes directly at its landing site. But what it did observe provided compelling confirmation that methane lakes had, without a doubt, once existed there. Huygens landed on what unmistakably appeared to be a dried-up lake bed. The very stones you can discern in the surface photographs, captured in that dim, alien light, are rounded stones, remarkably similar to the pebbles found at the bottom of a riverbed or a lake here on Earth, smoothed and polished by the relentless flow of liquid. From the majestic perspective of space, the Cassini orbiter was indeed able to confirm that active methane lakes are still found on Titan today, vast liquid bodies shimmering in its perpetual twilight. Near the moon's south pole, Cassini observed a specific area which was later definitively confirmed to be a lake aptly named Ontario Lacus. This lake, still remarkably large at 15,000 square kilometers, is approximately 20% smaller than its North American namesake, Lake Ontario, a true alien inland sea. On one side of this lake, a smooth shoreline, gently eroded by waves, can be clearly seen, a familiar terrestrial feature in an alien landscape. On the west side, even more astonishingly, Cassini captured the first evidence of a river and a delta on Titan, a profound geological discovery. This implies that liquid hydrocarbons indeed flow down from higher planes, carving channels as they wind their way to the lake, leaving behind distinct delta deposits through much the same process that we find operating on Earth. Ontario Lacus, despite its size, is remarkably shallow, estimated to be only between 40 centimeters and 3 meters deep, with its deepest point likely just over 7 meters. As Cassini's radar meticulously mapped this lake, it revealed an intriguing detail. The lake did not have waves bigger than 3 millimeters, meaning its surface would appear like a sheet of glass, or a perfect mirror. This doesn't necessarily mean there can't be bigger waves, unless this liquid is particularly viscous. More likely, it was simply not a windy day when these crucial observations were taken. Given Titan's dense atmospheric density and its lower gravity, theoretical models suggest that waves on Titan should, in fact, be significantly bigger than they would be on Earth, a subtle interplay of forces creating different wave dynamics. As the north pole of this intriguing moon began its long, gradual emergence from a 15-year-long winter, another magnificent lake was quietly discovered, Jingpo-Lacus. As Cassini was gracefully passing by the moon, a rare and beautiful cosmic alignment occurred. Sunlight, breaking through the perpetual haze, was perfectly reflected off the glassy surface of Jingpo-Lacus, beaming like a mirror directly into Cassini's waiting view. Upon further meticulous observation, Cassini was able to detect even more compelling evidence of moving liquid on Titan, as clearly evidenced by the winding rivers flowing into the lake. The second largest lake on Titan to be discovered is Ligeia Mare, found prominently in the moon's north polar region. This colossal body of liquid is even bigger than Lake Superior on Earth, encompassing a staggering surface area of 126,000 square kilometers. While parts of this immense lake are reasonably shallow, its average depth is considerably deeper than Ontario Lacus, reaching an estimated 50 meters. And in some of its profoundest parts, it could reach depths of over 200 meters, a vast, hidden sea indeed. Plenty of rivers can be seen gracefully flowing into this great lake. And there are also large, distinct islands scattered around this area. Here, we encounter a particularly curious observation Cassini made. one that scientists have dubbed the Magic Island. This refers to the mysterious appearance and disappearance of what seemed to be an island within the lake's expanse. While scientists are still unsure exactly what happened here, the leading theories gently suggest several possibilities. It could be silt, tiny particles of sediment, suspended within the lake, temporarily visible, or perhaps bubbles of gas rising to the surface, creating a transient feature. Another intriguing idea is that subsurface ice, once anchored, might have risen to the surface as the lake warmed during the moon's spring. Whatever its cause, this fleeting magic island remains a very curious enigma. But the true monarch of Titan's liquid landscape, the largest of them all, is the colossal Kraken Mare. This immense body of liquid stretches for a staggering 400,000 square kilometers, a truly vast alien ocean. As you can observe, this immense lake is split into two main parts, gracefully separated by a small, narrow stretch of liquid, quite similar in appearance to Earth's Strait of Gibraltar. This narrow passage has earned it the intriguing nickname of the Throat of the Kraken. Due to the immense size of the lake and the subtle influence of tidal forces from Saturn, it is thought that the tide within Kraken Mare changes by about 1 meter. Consequently, this strait may experience strong currents and even, perhaps, powerful whirlpools, making it a dynamic, turbulent gateway. Kraken Mare is also quite deep, especially when compared to the shallower Ontario Lacus, but it isn't thought to be any deeper than 170 meters. So, we have now whispered about the magnificent lakes on Titan, these vast bodies of liquid methane and ethane, but what other interesting surface features might this enigmatic moon possess? Well, plenty. Actually, Titan's surface is, in geological terms, quite young, estimated to be as young as a mere 100 million years old. This youthfulness implies that its surface must be geologically active, constantly being reshaped and renewed. Some scientists gently believe that the dirty ice crust of Titan is substantially rigid, a firm shell. However, there is also some intriguing evidence to suggest the presence of tectonic activity on the moon, possibly caused by those relentless tidal forces from Saturn. But the main factor responsible for Titan's continually renewed surface is likely the very same process that replenishes the methane in its atmosphere, cryovolcanoes. Now, this is truly fascinating. You know how magma on Earth is incredibly hot, but when it erupts from the ground, it eventually freezes, forming new rock. Well, Titan experiences a profoundly similar phenomenon, but with an alien twist. Its magma is not superheated silicate rock, but rather a cold, viscous mixture of water and ammonia. And when this cryomagma erupts from the cryovolcanoes and spills across the land, it too freezes, not into rock, but into a form of new, exotic ice, perpetually renewing the surface. Because this blend of water and ammonia is significantly less viscous than Earth's molten lava, it flows much further, creating vast, expansive plains. This implies that mountains on Titan are generally more flat and will never reach the immense heights of volcanoes we see here on Earth. While it is challenging to confirm specific cryovolcanoes on Titan due to the profound obstruction caused by its thick atmosphere, the most likely candidate, the best fit we have, is Sotra Patera, found in the southern hemisphere. In the images we have, its height has been exaggerated by a factor of 10, but it still gives a good idea of the immense size of the dome and the 1.7 kilometer deep pit, the largest we currently know of on Titan. The sheer force necessary for such an eruption would have been incredible, and while it doesn't appear to be actively erupting now, it is being actively monitored, a silent giant awaiting its next awakening. The very fact that lava on Titan is a mix of water and other minerals means that its surface could be aptly compared to dirty ice, a landscape of frozen, chemical-rich slush. Because the Huygens lander famously bounced and wobbled in a specific way as it finally came to rest on Titan, we now have a rough idea of what the consistency of its surface might be like. Scientists have gently referred to it as akin to soft, damp sand, a pliable, somewhat yielding terrain. Another intriguing theory suggests it's more like snow, with a thin, brittle crust on top. Imagine walking on frozen snow. Here on Earth, if you're careful, you can glide across a solid surface, but if you stomp too hard, you will sink in quite deeply. Titan's surface is believed to be something akin to this, a delicate balance between firm crust and yielding subsurface. Titan's highest mountains manifest in the form of ridge belts, reminiscent of the vast mountain ranges like the Rockies in America. These immense ridge belts could themselves also be a form of cryovolcanoes, vast, linear eruptions of icy material. The single largest mountain on Titan can be found within one of these impressive mountain ranges, known as Mithrim Montes, and it reaches a towering 337 meters high. Interestingly, mountains of this immense height are thought to be perpetually topped with methane snow, a unique form of precipitation in this frigid alien world. Also found on Titan are many deep gorges, vast valleys, and colossal dunes, shaped by its unique atmospheric conditions. Using infrared cameras, which can peer through the obscuring haze to see the surface from space, what can also be seen quite prominently are these large patches of dark terrain. Originally, these dark patches were thought to be vast seas of liquid hydrocarbons, as they appeared so dark and flat. However, the Huygens probe, in its brave descent, landed directly on one of these areas, a region known as Shangri-La, and discovered it to be solid ground. While they could very well have been ancient seas in the distant past, they are now vast plains of dark mineral deposits, strikingly similar to the famous Namib Desert on Earth, where they appear as immense, wind-swept dunes in some places, sculpted by the gentle, persistent alien winds. Overall, Titan, despite its profoundly alien nature, can be compared to Earth in a surprising multitude of ways. Scientists often believe that Titan shows us what early Earth might have been like, albeit in a much colder, more frigid state. It is fair to say that Titan is remarkably, captivatingly interesting, a world that continually sparks our scientific curiosity. One can only hope it gets its own dedicated mission one day. Cassini, that valiant orbiter, did a truly magnificent job of surveying the Saturnian system, but it was never exclusively a Titan orbiter, and its mission, sadly, has now concluded. What would be incredibly fascinating is a future probe designed specifically to explore more of Titan's complex surface, perhaps even venturing across its methane seas. And one can only hope that it won't be long until a mission with such ambitious goals will be approved, allowing us to delve deeper into its shrouded mysteries. Until then, we can only whisper about the wonders of Titan. Having lingered in the unique, hazy twilight of Titan, a world shrouded in mystery and liquid hydrocarbons, our quiet cosmic journey now carries us back towards the heart of the Saturnian system. Here, nestled amongst the countless icy fragments of Saturn's magnificent rings, lies another celestial body that, though relatively small and often unassuming in natural light, reveals itself to be one of the most intriguing objects in our entire solar system. This is Enceladus, Saturn's sixth largest moon. From a distance in the soft embrace of sunlight, it appears as little more than a pristine, white orb. Yet, beneath this tranquil exterior, there is so much more to Enceladus than meets the eye. It is an active, icy world, a dynamic sphere constantly reshaping itself, with breathtaking jets of water vapor pouring out from its southern hemisphere, a clear, undeniable sign of a furious internal life. Thanks to the truly remarkable Cassini spacecraft mission, humanity has been able to study and observe Enceladus in exquisite, unprecedented detail. We perhaps know more about its inner workings than some of the larger and seemingly more accessible Jovian moons. However, while we have glimpsed so much from its exterior, it is the enigmatic interior of this moon that still holds countless mysteries, beckoning us to unravel them. I am Alex Mullen, and you are peacefully watching Astronomy. In this quiet moment, together, we will explore some of the most fascinating details of Enceladus, piecing together the vibrant photographs and invaluable data from a variety of missions to uncover almost everything you could ever wish to know about this special, enigmatic moon. So, settle in and let us embark upon this gentle journey of discovery. Let us begin by quietly discussing where Enceladus fits into the grand, intricate tapestry of our solar system. Enceladus is currently recognized as Saturn's 14th closest moon. I say currently, with a soft whisper, for Saturn, with its vast, complex ring system, harbors some tiny, almost invisible moonlets hidden within those very rings, small companions that may or may not, in the future, be formally classified as moons. However, Enceladus holds a more prominent position. It is the second closest major moon to Saturn itself, second only to the mysterious cratered Mimas. This close proximity means that its orbit carries it just outside of Saturn's main, majestic rings, a delicate dance at the edge of the cosmic spectacle. Its orbit follows the intricate planes of the rings with remarkable precision, a testament to the powerful gravitational forces at play. Enceladus completes one full orbit around Saturn in a surprisingly swift 33 hours, a hurried waltz around its colossal parent. Interestingly, and crucially for its very existence, Enceladus is locked in a 2-1 orbital resonance with Dione, Saturn's fourth closest major moon. In simpler terms, this means that Enceladus completes exactly 2 orbits around Saturn in precisely the same amount of time that Dione completes one. This elegant, mathematically precise orbital resonance is believed to prevent Enceladus's orbit from ever becoming perfectly circular, a gentle, unyielding push and pull. Instead, it forces Enceladus to undergo continuous tidal deformation, a subtle stretching and squeezing as it moves closer to and then further from Saturn. This constant internal kneading is profoundly significant, for it generates immense heat within Enceladus's core, a hidden furnace powered by gravitational forces, warming its depths from within. You see, as far as our instruments and observations can tell, Enceladus's outer surface is predominantly composed of clean water ice, pure and unblemished, with little to no rocky impurities or other foreign materials. Because Saturn itself is situated so incredibly far away from the Sun, receiving only a faint trickle of solar warmth, the outer layer of water on Enceladus has long since frozen over completely. Enceladus is, in essence, a frozen ocean world, a giant, shimmering ball of solid water ice. Because it is largely free from other materials on its surface, its pristine, icy shell reflects nearly all the sunlight that reaches it. This makes the moon one of the whitest objects in our entire solar system, possessing a remarkable bond albedo of 0.81, which is nearly as high as fresh, fallen snow here on Earth. As such, it is also, paradoxically, one of the coldest satellites of Saturn, with a noon temperature plummeting to an average of -200 degrees Celsius. The very whiteness of its surface, reflecting a large percentage of the faint sunlight back into the frigid expanse of space, contributes to its extreme cold. However, the true magic, the profound secret of Enceladus, lies deeper, approximately 30 to 40 kilometers down. Beneath this incredibly cold, pristine surface, immense pressures begin to build. And the heat energy generated from the relentless tidal deformation of its orbit has raised the temperature of the water ice to a critical point. At this remarkable depth, the water can actually exist in a liquid form. It is widely believed that there is an entire mantle, a global ocean of water, upon which the solid ice crust of Enceladus gently rests. This is a profound concept, reminiscent of the magma mantle upon which our own Earth's rocky crust floats. At the very least, even if it is not a truly global ocean, scientists confidently expect there to be an immense pocket of liquid water beneath the moon's south pole, a vast, hidden sea tucked away in the cold. How do we know this with such certainty? Well, the most obvious and compelling indication comes from the spectacular, gargantuan plumes of water that are constantly being ejected from the deep cracks in Enceladus's crust, a breathtaking phenomenon that scientists refer to as water or cryovolcanism. These jets are not merely passive trickles, they are incredibly active, consistently blasting around 250 kilograms of water into space every single second at astonishing speeds exceeding 2,000 kilometers per hour. This is an immense, forceful expulsion. The power of these eruptions is so great that most of the water vapor particles, once ejected, easily escape Enceladus's relatively weak gravity. They then drift, captured by Saturn's immense gravitational pull, and eventually coalesce into orbit around the ringed giant, slowly forming Saturn's diffuse ethereal E-ring. This particular ring around Saturn is very diffuse, meaning it is not dense and solid like the main rings. As a result, it is not readily visible to our eyes unless it is backlit by the distant sun. From this unique angle, with the faint sunlight shining directly through the countless tiny water particles, the E-ring appears exceptionally, almost impossibly blue. In fact, this ring is considered the bluest object in our entire solar system, even more so than Neptune, that distant cerulean giant. The remarkable uniformity of the E-ring's shape is also heavily influenced by the constant orbital dance of Enceladus. Enceladus's plumes create delicate, ephemeral tendril shapes within the rings as more material erupts from its interior. However, these newly formed sections of the ring tend to smoothly diffuse and blend back into the broader ring as Enceladus gracefully moves further away along its orbit, a continuous process of creation and dispersal. During the extensive course of the Cassini mission, that tireless explorer of the Saturnian system, the spacecraft was able to perform a truly daring feat. It actually passed directly through these plumes, intentionally flying through the very jets of water being ejected from Enceladus. This allowed Cassini's sophisticated instruments to detect the precise substances being ejected from them, offering a direct, invaluable sample of Enceladus's hidden interior. While Cassini was not originally designed with these plumes in mind, scientists didn't even know about their existence until Cassini arrived at Saturn. It was fortuitously equipped with an instrument called the Cosmic Dust Analyzer. This instrument, intended to analyze tiny dust grains in orbit, proved remarkably versatile and was able to meticulously analyze the particles within Enceladus's plumes. While it may not have given us the full, complete picture of everything contained within these particles, it nonetheless provided profound insights. Water, as expected, was the predominant substance detected, but, astonishingly, amino acids, carbon dioxide, and methane were also unequivocally found. The presence of amino acids is profoundly significant. They are, as we understand them, the very building blocks of life here on Earth, the fundamental organic molecules from which proteins and, ultimately, living organisms are constructed. These vital compounds are notably found around the thermal vents at the bottom of Earth's own oceans, where life thrives in perpetual darkness, drawing energy from chemical reactions. This immediately leads us to the most tantalizing, most whispered question. Does this mean Enceladus possesses thermal vents of its own deep beneath its icy crust, on its ocean floor? And if so, do these vents harbor their own unique ecosystems of life, thriving in the perpetual twilight of a distant moon? While the evidence for an underground ocean is abundant and compelling, scientists still aren't completely sure about the precise internal structure of Enceladus. At some points in the past, scientists believed that Enceladus might have been entirely composed of water, all the way through, a giant ice ball. However, more recent data from Cassini suggests that Enceladus's mass is in fact greater than previously thought, implying that it must contain a significant amount of denser material, likely iron or silicate material, within its core. Scientists are increasingly leaning towards the theory that the internal structure of Enceladus is indeed differentiated, meaning it is a celestial body with distinct, defined layers within it, much like Earth, despite its relatively small size. An object of Enceladus's scale, at only about 500 kilometers across, is right on the borderline of being in hydrostatic equilibrium, or in other words, being rounded into a spherical shape by its own gravity. There are, in fact, a number of other celestial objects of similar or even smaller sizes that are not in hydrostatic equilibrium, retaining more irregular, potato-like shapes, such as Neptune's moon Proteus. In any case, assuming Enceladus does indeed possess a differentiated interior, this core is likely to be predominantly rocky. This is a crucial detail for the potential for life, as any thermal vents in Enceladus's vast water ocean would necessarily have to originate from a rocky core. A rocky ocean floor would also serve to provide essential nutrients and minerals, elements that we believe life would profoundly need to form, develop, and thrive. Thermal activity clearly does exist on Enceladus, evidenced by the plumes themselves, and the detection of amino acids within those plumes strongly suggests the presence of a rocky core interacting with the liquid water. As Cassini, our tireless robotic observer, gracefully passed over Enceladus, it also meticulously mapped out the thermal emissions from the moon's surface, revealing its hidden heat signatures. It turned out that the locations of the powerful jets of water perfectly line up with what has come to be known as Enceladus's tiger stripes. These are immense, prominent depressions, roughly 130 kilometers long, 2 kilometers wide, and 500 meters deep. It is widely believed that these are profound tectonic fractures in the moon's thick, icy crust, vast cracks that reach deep into its interior, providing pathways for the cryovolcanic eruptions. What is truly interesting about the surface features of Enceladus is the almost complete absence of impact craters across its southern hemisphere, and very few anywhere else on the moon. This stark lack of craters implies that Enceladus's surface is very young, constantly being renewed and resurfaced. While Enceladus does possess a thin atmosphere formed from the ejected water from its plumes, this atmosphere is nowhere near dense enough to burn up asteroids before they strike the surface. Instead, a portion of the water from the plumes obviously settles back down onto the surface, gently smoothing it off over time, erasing the scars of impacts. This ongoing resurfacing is another reason why Enceladus is so remarkably round for such a small celestial body. In fact, apart from the prominent tectonic fractures and the few scattered craters, Enceladus's topographical variation is remarkably minimal. There are no significant mountain ranges to speak of, though if you zoom in far enough, you might perceive what you could call a rough terrain around the South Pole, a subtle texture in the ice. This is perhaps the highest resolution image we possess of its surface, and as you can clearly see, it truly does appear like a giant, ancient glacier, sculpted by slow, immense forces. It is interesting to note that even in this small view, there are some perfectly smooth sections of ice, interspersed with more jagged, fractured regions over the North Pole. A clear difference emerges: the number of craters present there is significantly higher. While there are tectonic fractures here too, there are no active plumes on this side of the moon. Thus, the surface here is clearly much older than the actively resurfaced South Pole, which is why it retains more of a cratered, ancient surface, a silent contrast reflecting the moon's internal dynamics. As Cassini valiantly flew directly through the plumes emanating from Enceladus's South Pole, it also seized the invaluable opportunity to image the surface very closely around the enigmatic tiger stripes. The surface here is utterly incredible, a landscape unlike anything you would have ever seen on Earth. It appears as though the very ice has been folded, squashed, and shifted around, leaving behind these remarkable fracture lines and intricate formations etched deeply into the surface ice. The very fact that Cassini was able to get so incredibly close to Enceladus is a monumental feat in and of itself, a testament to human engineering and scientific daring. It is truly fantastic that we can possess such an intimate, close-up view of something so far away, a profound glimpse into a distant, active world. Unfortunately, however, since the magnificent Cassini mission has concluded its journey, we no longer possess any active spacecraft in orbit around Saturn that can continue to study Enceladus in such detail. While there have been plenty of ambitious mission proposals in the past to return to this intriguing moon, all of them, sadly, were canceled before they could ever come to fruition. What would be truly incredible, a profound leap in our understanding, is a future probe that could either somehow make its way directly into Enceladus's hidden ocean, or at the very least, consistently search the plumes for irrefutable signs of life, perhaps even collecting samples for return to Earth. While there is already a mission called Dragonfly planned to journey to the nearby moon of Titan, this mission will, by design, have nothing to do with Enceladus. So, although a couple of new mission proposals are currently under careful review to return to Enceladus, this means that we are, unfortunately, still a couple of decades away, at the very least, from unlocking its deepest secrets. This is a quiet shame, isn't it? Because who knows what profound secrets lie patiently in wait, hidden just beneath that icy crust, beckoning us to discover them. Having lingered in the captivating, cryovolcanic embrace of Enceladus, its plumes whispering secrets of a hidden ocean, our cosmic journey now stretches even further, beyond the majestic realm of Saturn, into the deep, quiet reaches of the outer solar system. Our gaze falls upon Uranus, a planet often perceived as a serene, featureless blue orb, yet attended by its own collection of peculiar moons, and among them, one tiny, unassuming world stands out, not for its size, but for a dramatic, almost theatrical feature that utterly defies our earthly expectations. This is Miranda, one of Uranus's smallest, yet most topographically bizarre moons. Imagine, if you will, a scene painted by the very brush strokes of the cosmos, a moment suspended in the silent void. The setting is stark, profound. Your arch rival, a figure of tension in this vast, tranquil expanse, has you cornered, a gun, a cold glint of metal, pointed unyieldingly at you. Your back is to the precipice, overlooking a drop so immense, so utterly unimaginable, that it beggars belief. This is Verona Rupes, the tallest cliff face in our entire solar system. Picture it, a sheer, terrifying drop of 20 kilometers. To truly grasp the scale of this cosmic chasm, consider that it is roughly 16 times larger than the tallest cliff face we know here on Earth. Mount Thor in Canada, which, mighty as it is, measures a mere 250 meters. Your only slender advantage, your single, fragile hope, in this dire moment is the realization that you are standing on Miranda, a tiny moon, only 470 kilometers wide. This means the gravity here is astonishingly weak, a mere whisper compared to Earth's embrace. So, the question hangs in the silent, cold air. Do you make the leap, trusting the vast, gentle emptiness below, and take your chances with the monumental drop, or do you remain to face the immediate threat of the gunman? Let us ponder a few factors, allowing the science to guide our imagination. Miranda, as we softly observed, is indeed the smallest of the 5 circular moons of Uranus. At just 470 kilometers across, it exists right on the very edge of what scientists call hydrostatic equilibrium. In simpler terms, this means it is just barely massive enough to be pulled into a roughly spherical shape by its own very weak gravity, a cosmic sphere teetering on the brink of irregularity. Its composition further contributes to its ethereal nature. It is not very dense, thought to consist of at least 60% water ices. This high ice content, coupled with its diminutive size, culminates in an incredibly weak gravitational pull. For a tangible comparison, let us recall that here on Earth, gravity relentlessly accelerates you towards its surface at 9.8 meters per second squared. On our own moon, that comforting pull is significantly reduced to 1.6 meters per second squared. But on Miranda, the acceleration is a mere 0.08 meters per second squared. This profound difference means that, should you choose to leap from the edge of Verona Rupes, you would experience an incredibly gradual descent towards the bottom, a prolonged, almost dreamlike fall, rather than a sudden plummet. But there is another critical factor to consider in this cosmic calculus. Here on Earth, if you were to fall from a great height, after a certain distance, you would eventually reach what we call terminal velocity. This occurs when the upward force of air resistance precisely combats the downward acceleration of gravity, meaning your speed would eventually cap out. In a typical lying position, for instance, this terminal velocity is around 200 kilometers per hour. However, Miranda, being a tiny airless world, possesses no atmosphere, and this crucial absence means there would be no air resistance whatsoever to slow your fall. So, while your initial descent would indeed be remarkably slow, a gentle float into the abyss, your speed would inexorably begin to pick up, accelerating steadily with nothing but the distant base of the cliff to eventually bring you to a halt. The sheer scale of Verona Rupes, that massive 20-kilometer tall cliff, makes this a truly profound consideration. Such an astonishingly tall cliff can exist on Miranda precisely because its gravity is simply not strong enough to pull it down into a flatter, more stable formation. We don't really know for certain how it formed in such a dramatic fashion, as Miranda should theoretically be too small for the grand, planet-shaping dance of plate tectonics. One intriguing theory, however, suggests that water, hidden beneath Miranda's icy crust, froze and then expanded with immense force, causing the moon's outer surface to split and rupture, creating these colossal canyons that stretch for hundreds of kilometers long, silent scars of a profound internal upheaval. So, let's return to our scenario, to that pivotal leap from the edge, a 20-kilometer drop, with an acceleration of merely 0.08 meters per second squared. You may not be surprised to discover that it would take you an incredibly long time to reach the bottom of that cliff. Not seconds, not minutes, but 12 whole minutes. Imagine that 12 minutes of slow, deliberate falling through the silent, cold vacuum of space, a profound journey into the abyss. This means it certainly wouldn't be a dramatic, split-second escape like those seen in action films, where a hero swiftly jumps off a dam before their pursuer can react. Your arch-rival, the gunman, would have to be remarkably slow, astonishingly unobservant, to allow you to make that 12-minute leap before he could fire. And should that long, slow fall somehow go well, by the time you finally reach the base of Verona Rupes, with absolutely no atmosphere to slow your descent, you would be traveling at a considerable 200 kilometers per hour. A parachute would be utterly useless here, providing no drag whatsoever. But perhaps a really large airbag, or a series of tiny, perfectly timed retro rockets, might just do the job, cushioning your final impact, allowing you to survive this most audacious of escapes. It is a profound thought, isn't it? The unique physics of such a tiny, distant world offering both immense peril and a strange, drawn-out chance for survival. As Miranda's unique, cliff-scarred form fades gently from our view, our long, quiet journey carries us even further into the cold, distant reaches of our solar system, to the outermost known giant Neptune. And here, accompanying this deep blue world, lies a moon that is truly and exceptionally unusual, though often forgotten, celestial body. This is Triton. It possesses so many unique characteristics, so many profound anomalies, that it undeniably makes it one of the most interesting objects in our entire solar system. Yet, precisely because it is the largest moon of Neptune, the planet furthest away from our sun and from Earth, it means that humanity has only ever visited it once, and then very briefly. This fleeting encounter occurred during the extraordinary journey of Voyager 2 all the way back in 1989, more than 3 decades ago. What did that single precious visit reveal to us about Triton? And what have we quietly gleaned about it in the years since, through distant observations and meticulous analysis? I am Alex Mullen, and you are peacefully watching Astrum, and together, in this quiet contemplation, we will uncover everything there is to know about the fascinating, enigmatic world of Triton. First, let us gently discuss where Triton finds its place within the grand architecture of our solar system, and more specifically, within its local planetary system around Neptune. Triton is one of 14 known moons of Neptune. 7 of these moons are what we categorize as regular moons, meaning they orbit along Neptune's equatorial plane. It's ecliptic, with very circular orbits, or orbits with incredibly low eccentricity, almost perfect circles. Beyond these inner regular moons, we encounter a collection of irregular moons. And the very first of these, the most prominent, is Triton. An irregular moon is defined by its unusual, often wild orbit. It typically follows an inclined path, an eccentric, non-circular trajectory, and often, crucially, a retrograde orbit. This latter characteristic is where Triton truly sets itself apart from almost any other spherical moon in our solar system. It possesses an irregular orbit. Imagine this: Triton orbits clockwise around Neptune, while Neptune itself rotates counterclockwise. This inverse motion, this cosmic defiance, is remarkable. Furthermore, Triton's orbit is highly inclined, set at a dramatic 130-degree angle to the ecliptic plane of Neptune. Though it is worth noting, amidst this orbital rebellion, that its orbital eccentricity is remarkably close to zero. Its path is almost perfectly circular. All other large moons in our solar system are regular moons, faithfully orbiting in the same direction as the rotation of their parent planet, in harmony with their formation. This profound inverse orbital motion, this highly inclined retrograde path, heavily implies a startling truth: Triton did not form alongside Neptune. No, it is, in fact, a captured object, a wanderer from the outer reaches of the solar system, gravitationally snared by Neptune's immense pull. Specifically, scientists believe it was once a captured dwarf planet, a world that once roamed free in the distant cosmos. It is no wonder, then, that Triton is by far the biggest of Neptune's 14 moons, dwarfing all its companions. It comprises an astonishing 99.5% of the total mass found within Neptune's entire orbit. But how large is that truly? In scales we can relate to, in quiet comparisons. Well, it holds the distinction of being the second largest moon in relation to its parent planet, surpassed only by our own Earth and its proportionally immense moon. While Triton is actually slightly smaller than our own moon in absolute terms, it orbits closer to Neptune than our moon orbits Earth, which means that if you were to stand on Neptune, Triton would appear to be about the same size in the sky as our moon appears to us. It is the seventh largest moon in our entire solar system, a truly significant celestial body. And most interestingly, it is definitively bigger than Pluto. Pluto, that distant, beloved dwarf planet, is often considered the king of the Kuiper Belt, the largest object we know of that formed in that icy, remote region. That is, until we consider the profound possibility that Triton once, long ago, ruled that very area, a majestic body in its own right, before Neptune, with its irresistible gravitational allure, captured it. Further compelling evidence supporting this profound idea was found when the New Horizons spacecraft gently swept past Pluto in 2015. The data it collected strongly suggested that Triton and Pluto share a near-identical composition, a striking similarity that powerfully supports the theory that they share a common origin, both born in the frigid, distant reaches of the Kuiper Belt. Beyond Triton, in Neptune's outer domain, are 6 other irregular moons, found much, much further out. They are almost certainly captured objects as well, their orbits unusually eccentric and often taking years to complete a single circuit around Neptune. These distant, chaotic companions were probably perturbed into their wild, weird orbits by the very same immense gravity of Triton during its initial capture. It is a cosmic domino effect, a powerful testament to the influence of a large, newly acquired moon. So, if Triton was indeed a captured object, a former dwarf planet from the distant Kuiper Belt, how exactly did that happen? Celestial objects need to lose momentum to be captured. Otherwise, they would simply possess enough kinetic energy to escape a planet's gravitational grasp and continue on their way. Well, we cannot know for sure. Of course, the precise, intimate details of that ancient cosmic event. But the leading theory right now, the most compelling whisper from the past, suggests that Triton was once part of a binary system, perhaps like Pluto and its relatively large companion, Charon. Imagine 2 distant worlds, locked in a gentle, gravitational dance with each other. As Neptune, with its immense, irresistible gravitational field, approached Triton and its companion moon, the immense gravity from this close encounter would have caused the binary system to dramatically fall apart. Triton's companion moon would have been violently slingshot away into the vastness of space, forever lost from the system. And in that very same chaotic interaction, Triton itself would have lost just enough momentum to be gravitationally snared, to be captured in a new, albeit strange, orbit around Neptune, becoming its largest and most intriguing moon. I mentioned that Triton shares some striking characteristics with Pluto, a quiet kinship despite their separate fates. What exactly does that entail? Well, both worlds possess a predominantly nitrogen ice surface, a vast, frozen expanse of solidified atmospheric gas, subtly mixed with other exotic ices, such as water and carbon dioxide. Triton, in its own rugged way, has quite a flat terrain overall. Its topography, its gentle hills and valleys, rarely varies by more than a kilometer. However, despite this overall flatness, Voyager 2 did observe intricate ridges and troughs, vast plateaus, and expansive ice plains, subtle variations in its frozen landscape. What you may find particularly unusual, however, is that Triton possesses very little in the way of craters. This profound lack of impact scars implies that its surface is remarkably very young, constantly being renewed and resurfaced by active geological processes, much like Earth, or Io, or Europa, like Pluto. Triton also exhibits some intriguing reddish patches on its surface. These are thought to be caused by methane ice, which, upon reacting with the energetic ultraviolet light from the sun, produces complex organic compounds known as tholins. Imagine a tar-like consistency, a subtle reddish residue staining its icy plains. While the presence of organic compounds does not automatically imply the presence of life, these are the basic chemical building blocks from which all known life forms are constructed. Life, as we currently understand it, likely could not exist on the surface of Triton anyway, as it is simply far too cold, and the sun is far too dim to support any life form that we can presently imagine. But what is truly interesting, what truly sparks our deepest curiosity, is what could potentially be found under Triton's crust. Our quiet contemplation of Triton's origins, that distant cosmic drama of capture and transformation, now leads us to peer beneath its frigid, enigmatic surface. For it is here that scientists believe some of its most profound secrets reside. Underneath Triton's outermost layer, a realm thought to be composed primarily of rock and metal, gives Triton a reasonably high density for a moon, weighing in at approximately 2 grams per cubic centimeter. Because of this relatively dense composition, and due to the significant leap in size, it represents from the next biggest moon in the solar system, Titania. A companion of Uranus, Triton surprisingly holds more mass than all the moons smaller than it in the entire solar system combined. Imagine that a single moon, nestled so far from our sun, yet containing a greater gravitational pull than a multitude of its smaller, icy cousins. Deep within this rocky, metallic heart, scientists theorize that the radioactive decay from its rocky core could be generating enough internal heat to warm and power convection currents within a vast subsurface ocean of water. This is a concept we've encountered before in our gentle journey, a recurring whisper of possibility beneath the frozen shells of distant moons, much like what is thought to lie beneath the surfaces of Europa, Enceladus, and some other large moons throughout our solar system. And just like Europa and Enceladus, the phenomenon of cryovolcanism is an active process today on Triton. Imagine liquid water, perhaps enriched with minerals, from this hidden mantle erupting onto the surface, much like lava here on Earth. As it flows out into the extreme cold of Triton's surface, this liquid quickly freezes, perpetually renewing Triton's ancient face. Indeed, our intrepid probes have already identified some very young lava plains on Triton. These appear as sparse, remarkably flat regions, yet interestingly, they are often bordered by a distinct wall that surrounds the entire plain. These formations are called plana, or, in simpler terms, solidified lava lakes, vast frozen seas of once molten cryomaterial. We also clearly see cauldrons, immense collapsed depressions found at the center of a cryovolcano, the very source from which those vast lava plains flowed. It is thought that the water from these powerful eruptions would have also brought precious minerals from the underground oceans onto the surface. This is a crucial detail, for these minerals, interacting with the sparse sunlight, might even be the very source of the tholins and other organic matter we discussed earlier, painting Triton's surface with those mysterious reddish hues. If this is indeed the case, and if these complex organic compounds are found not just on the surface but also within the subsurface ocean, then it implies a tantalizing possibility the conditions within that hidden ocean might be precisely right for life to have been able to form and evolve there, a quiet, distant cradle of potential existence. We also observe long lines permeating over the surface, vast linear features stretching across the frozen plains. These are likely faults, immense cracks in the crust, caused either by subtle tectonic activity or the relentless process of freeze-thaw weathering, reshaping the surface over eons. When we turn our gaze to some of the more detailed images captured by Voyager 2 of Triton, we can truly perceive the direct results of some recent eruptions, powerful events that have shaped its contemporary landscape. You'll notice what appears to be dark deposits on the surface, often in distinct cone or funnel-like shapes, some stretching up to 150 kilometers long. However, these smaller eruptions, while visually striking, may not originate directly from the deep mantle itself. Voyager 2, in its fleeting flyby, was fortunate enough to spot some of these plumes reaching a remarkable 8 kilometers high above Triton's surface, but these particular plumes are thought to be caused by a different, yet equally fascinating, mechanism, a solid greenhouse effect operating within the moon's icy crust. Imagine the surface of Triton consisting of a layer of relatively clear ice, which has settled subtly upon darker deposits, perhaps those very tholins we spoke of, absorbing the faint sunlight. The sun's weak rays shine through this transparent ice, gently warming the darker, more absorbent tholins beneath. This warmth causes the pocket of ice directly above the warmed tholins to sublime, transforming directly from a solid into a gas without passing through a liquid phase. As this ice sublimes, the pressure builds relentlessly in the trapped air pocket, pushing outwards, until finally, the surface layer above the pocket simply gives way, causing an explosive eruption. This powerful eruption also carries the dark deposits with it, spreading them outwards over the surface in those distinct patterns we observe. If this hypothesis holds true, a very similar process has been observed on Mars's poles, where carbon dioxide ice layers cover darker deposits, leading to subtle seasonal eruptions. This remarkable process, this delicate interplay of ice, sunlight, and hidden pressure, can only exist because of one crucial factor: Triton possesses an atmosphere. Although not as thick as scientists were initially expecting, Triton's atmosphere is present, albeit thin, measuring only 0.004 millibars. To put this into perspective, it's roughly equivalent to the atmospheric density found 80 kilometers up in Earth's atmosphere. However, like Pluto, this density varies significantly through seasonal changes. Since Voyager 2's observations, Triton's atmosphere has actually become slightly denser as the surface has warmed, causing a little more of the nitrogen ices on the surface to evaporate. However, when Voyager 2 swept past Triton, its atmosphere was still dense enough to support actual weather up to 8 kilometers above its surface. In one remarkable image, you can actually clearly see clouds on Triton drifting through its tenuous atmosphere. And going back to the image of the plumes, you can observe that the dark deposits from the eruptions all end up facing the same distinct direction, a clear indication of a prevailing wind in that specific region of the moon. Like Pluto, Triton's atmosphere is also notably hazy, the cause of which is thought to be the presence of hydrocarbons, complex organic molecules not yet broken down into tholins by the faint ultraviolet light from the sun. The constant depositing of organic compounds through cryovolcanism, the continuous evaporation and freezing again through seasonal variations, and the presence of a weather-rich, active atmosphere, all combine to make Triton a truly very dynamic world, constantly in flux, constantly remaking itself. Unlike most other moons in our solar system, it behaves far more like a dwarf planet than a mere moon, likely a celestial sibling of the more famous Pluto, forged in the distant, frigid depths of the Kuiper Belt. All of these factors combined make it, without a doubt, an exceptionally unusual moon, a unique testament to the universe's endless capacity for surprise. So there we have it. Dear friend, a gentle journey through some of the solar system's most remarkable, often overlooked, moons. We began with Jupiter's Galilean companions Io, a world consumed by internal fire, perpetually reshaped by colossal volcanoes and the immense tidal forces of its giant parent, Europa, a shimmering ice shell hinting at a vast, hidden ocean, a tantalizing whisper of life beneath its frozen surface, Ganymede, the majestic titan, larger than a planet, a world of ice and water harboring its own mysterious magnetic field, a profound puzzle in the cosmos, and Callisto, the ancient chronicler, its face scarred by billions of years of cosmic impacts, a silent testament to the solar system's earliest days, yet perhaps a future beacon for humanity's expansion. We then ventured further into the elegant realm of Saturn, encountering Rhea, a surprisingly reflective moon with its enigmatic ice cliffs and subtle atmosphere, a quiet beauty in the Saturnian dance. From there, we soared into the dense, hazy embrace of Titan, a truly unique world with its thick atmosphere and vast, liquid hydrocarbon lakes, a cosmic mirror to our own planet's water cycle. Then, to the stunning spectacle of Enceladus, a small, unassuming orb perpetually spewing geysers of water into space, whispering promises of a habitable ocean warmed by unseen forces. And finally, our long journey brought us to the distant, bewildering reaches of Uranus and Neptune, to Miranda, with its impossible, towering cliff faces, a testament to strange, unique geology, and to Triton, Neptune's captured giant, a retrograde world with its own icy volcanism and a constantly renewing, hazy atmosphere, a dynamic dwarf planet in disguise. Each of these worlds, though often overshadowed by the grand planets they orbit, reveals itself to be just as, if not more, interesting, complex, and filled with profound mysteries. They are not mere dots of light in the vastness. They are vibrant, active, and deeply enigmatic places, each telling a unique story of cosmic forces at play, of creation, destruction, and the endless dance of matter and energy. The beauty of this exploration lies not in finding all the definitive answers, but in the profound act of asking the questions, in allowing our curiosity to gently lead us into the unknown, to sit with the grand uncertainties, and to find a deep sense of wonder in the sheer scale and diversity of our cosmic neighborhood. As we conclude this quiet, whispered journey, allow your thoughts to slowly, gently drift away from the distant moons and back towards your own quiet space. Carry with you this sense of vastness, of profound beauty, and of the endless mysteries that still await our discovery. Let the echoes of these unique worlds, their silent dances and their hidden secrets, soothe your mind. There is a deep, comforting peace in contemplating the immensity of the cosmos, in understanding our small, yet significant place within it. Allow any remaining thoughts, any lingering worries, to simply float away, like dust motes in the gentle light. Breathe softly, and let the quietude embrace you. This is not medical advice, does not replace therapy, and is intended for relaxation and exploration only.